Right. Right. So, good evening to all. So, is audio, video, and other things are clear? Please confirm me. Yes. So, today we'll discuss day 4, 807-2021. Induction questions. Right. So, I think in my last class, I was discussing something about the types of slots. So, what is that we have observed is right. What is that we have observed is so slotting, which is made inside the core, will support the conductors. But the main problem what we are having with this slotting is the performance of the machine is going to be reduced. Why? Because whenever you are trying to make that slotting, or we call it a slot, so the air gap becomes non-uniform. Whenever that air gap becomes non-uniform, the flux distribution also becomes non-uniform, because of which the performance is going to come down. So for that, we need to discuss the different types of slots, their advantages and disadvantages before we conclude which slots are being used for induction machine. I think I was left till this point yesterday, I think. Please confirm me. Right. Fine. See, one of the student, anonymous attendee. Sir, we didn't get yesterday's notes. See, Baba, I don't know what is your name, anonymous attendee. So already have forwarded that notes to the schedule manager. You can speak to them, right? So already have forwarded that notes, and some of the students have personally WhatsApped me. Then I forwarded the notes to them, right? Please, you can collect from them, please, right? Fine. So now we are going to discuss what are called as leakage flux lines and what are called as mutual flux lines before we discuss the advantages and disadvantages of the three different types of slots. Let us proceed. So what are leakage flux lines and mutual flux lines? Are mutual flux. Mutual flux lines are mutual flux. So yesterday I told you that whenever the magnetic flux lines come across more than one reluctance path, definitely the magnetic flux lines will be dividing, right? So the division of these magnetic flux lines depends upon the reluctance of the path. The path with the low reluctance will carry more number of flux lines when compared to a path with high reluctance, right? So this is what we have discussed yesterday. So basing on this, let me explain what are called as leakage flux lines and what are called as mutual flux lines. See, I tell you one thing, whenever the magnetic flux line, they are trying to travel in air, they always try to see to travel low distance or smaller distance in air. Why? Because if they want to travel in longer distances, the reluctance in that path will be very high. For example, say I'm having a air of length some 1 centimeter and I'm having a air gap of length say 2 centimeter. So one flux line is coming here and one flux line is coming here. So which path will be offering high reluctance means the 2 centimeter path will be offering high reluctance. As such, these flux lines may take this path only, 1 centimeter path. Why? Because when compared to the 2 centimeter in air, that 1 centimeter in air will provide less reluctance and hence the flux lines will try to flow along that path. Is this point clear? Confirm me. Confirm me. Yes. Now, basing on this, I'll be explaining what are called as leakage flux lines and what are called as mutual flux lines. So, for convenience, what I'll try to do now means I consider a stator core with open slots. It is only for explaining leakage flux lines and mutual flux lines, but not to explain the so-called as the advantages and disadvantages of open and other. After this, we'll take up the other part, right? See, one of the student, just before I proceed, let me conclude. So one of the student has texted me, sir, you told that induction motor cannot run with the speeds equal to ns. Nr is not equal to ns. Then why the name asynchronous has come? See, Baba, already I told you that if the rotor speed is always equal to the field speed, then we name that motors as synchronous motors. Synchronous. That means the rotor speed will be always synchronous speed. If the rotor speed is not equal to synchronous and if it is less than synchronous, then we name that machine as a asynchronous. What is the meaning of asynchronous? Means other than synchronous. Other than. That means it never runs with a synchronous, it will run with a speed less than synchronous. Anyhow, once this construction section is over, when I'm talking about the working principle, you'll get a clarity that what is the speed less than ns. Just hold for some time. Right now, let me proceed. Now here I'll be considering a core with open slots, just with open slots like this. I'm considering a core with open slots like this. So open slot like this. I'm not drawing any slots in the rotor section. So if I'm trying to draw individual, let me consider one single view. So this single slot I'll consider just for explanation purpose. I'll consider a single slot like this. Single slot like this. I'm just ignoring the other slots like this. So this one is the rotor core. This one is the rotor core. So this length between the cores, we call it as a air gap. This length between the cores, the radial length or the perpendicular length, we call it as a air gap. So this is air gap length. Air gap length. Right? So that is the air gap length. Fine. Now, for our convenience, let me consider that this length is something like 10 centimeter, 10 mm, and this length, the air gap length is something like 1 mm. Let me consider just for analysis purpose. Why? Because when compared to the slot width, the air gap length will be less, right? Done. So what I'll try to do means I'll try to consider one conductor here. One conductor I'm considering. And this conductor is carrying the current into. Let us consider into. So let me consider into. Then you know that according to the right hand thumb rule, so every current carrying conductor will produce as a magnetic field. And if you want to know the direction of that magnetic field, then you need to call upon the right hand thumb rule. Right hand thumb rule. So I'll be going for this. See. Now let me consider one flux line. Somewhere it has started here. Somewhere it has started here. Somewhere it has started here. And it is approaching the air gap. So this is the air gap. As it is approaching the air gap, so in order to complete the closed path like this, it will find two ways. What is the first way? Without crossing the air gap, by crossing the slot, it can complete the path. Without crossing the air gap, via the slot, it can complete the path. So this is one possibility. The other possibility is it can cross the air gap and via the rotor core, again it can cross the air gap and it can complete the path. So how many possibility this flux line 1 have to complete the path means there are two possibilities. One possibility is without crossing the air gap, it can complete the path within the stator only. The second possibility is by crossing the air gap with the help of that rotor core, it can complete the path. Is it clear? Confirm me. Is it clear? Confirm me. Yes. Now let us consider if it has to cross, if it has to take this path. So which path I'm talking about? The stator path. If it has to take the stator path, what should be the length of air it has to travel along that path? So the length of air it has to travel along this path is 10 mm. So without crossing the area, it has to complete the path via this way. So what is the length of air it has to travel? 10 mm. Then the other possibility is it can cross the air gap. When it is crossing the air gap, what is the length of air it has to travel? 1 mm. And this is the rotor core. Again, from rotor core back to the stator, it has to travel 1 more mm. So in the second possible path, it has to travel only 2 mm in air. One is when it is traveling from stator core to rotor core. So here to here, it has to travel 1 mm in air, and this is the rotor core. When it is traveling back from rotor core to stator core, so it will be taking 1 more mm. So what is the total length? It is 2 mm. So finally, can I say this flux line to complete the path is finding two ways. One way is to complete within the stator, but if it has to complete within the stator, it has to travel 10 mm in air. If it is crossing the air gap, it has to travel 2 mm in air. So it is something like one path is having 2 mm air and another path is having 10 mm in air. So which path is offering low reluctance means the 2 mm path will be offering low reluctance. So that is the reason the first chance is the flux lines will try to take the 2 mm path. So 2 mm path means which path it is? Which path it is? The air gap. That means it has to cross the air gap and it has to move. Just let me draw. So here it will cross the air gap. Just let me reduce the size. It looks like thick. So from here it will start and it will come like this and it will cross the air gap and via the rotor core it will complete the path. It will complete the path, right? So like this, most of the flux lines will try to take that path only. Why? Because along that path, what should be the length of air they need to travel? So it is only the 2 mm path. So like that, most of the flux lines are taking that path. But luckily, when they are taking that path, even they are touching the rotor core also. They are passing via the rotor core also. But it doesn't mean that all the flux lines will take only that path. One or two flux lines will take the other path also. Which path? So this path. So the stator path. Why? Because the permeability of this path is not infinity. So this path. So you can see till this point, you can see till this point, till this point, till this point, there is no division. There is no division. Five flux lines are coming from the core, but when they are approaching the air gap, they see a change in reluctance. One path is offering 10 mm, the other path is offering 2 mm air or 8 path. So which one is offering low reluctance means that 2 mm. As such, most of the flux lines are trying to take the 2 mm path. So, but it doesn't mean that all the flux lines will be taking the 2 mm. One or two flux lines will be taking that stator path also. Is this point clear? Confirming. Is this point clear? Confirm all of you. Right, done. So now the magnetic flux lines which are linking with both stator and rotor core, we name it as mutual flux lines or we can name it as useful flux lines. Why? Because as this induction machine works on mutual induction principle, the mutual flux is responsible for transferring of power. More is the mutual flux, then more will be the power transfer. So here the magnetic flux lines which are linking with both stator core and the rotor core, we call it as mutual flux lines. The flux lines which are linking only with either stator core or rotor core, but not both, we call it as leakage flux lines, right? I hope this point is clear. Confirm me, I'll give the statement. Right, done. All right. Leakage are unuseful flux lines are those which are passing either through stator or rotor, but not both. Both. We call it as leakage flux lines, right? Then what are mutual flux lines means? The flux lines which are passing through both stator and rotor. So let me write the next point is mutual useful flux lines are those which are passing through both stator core. Sometimes some textbooks uses the terminology links, passes through both stator core and rotor core. Mutual or useful flux lines are those which passes through both stator and rotor core, right? So here, can I say this blue color are mutual flux lines? Mutual flux lines, and this pink color is leakage flux lines. Why? Because it is linking with only one section. Leakage flux lines are leakage flux. I hope this point is clear. So who is it deciding? Means no one is deciding, but the magnetic flux lines, when they are approaching the air gap, they sees a change in reluctance. Whenever they sees a change in reluctance, then you can see the flux lines, they divides by their own basing on the reluctance of the path. The path which is offering low reluctance will be carrying more flux lines, the air gap path, and hence this we call it as mutual flux lines. The other one we call it as leakage flux line. Is it clear? Confirm me, all of you. Raise the hands now. Right. But it doesn't mean that so these mutual flux lines are having love and affection with the rotor. That is the reason they are going and linking. No. But as the rotor path is offering low reluctance, they are traveling via the rotor core. But unfortunately, if I'm trying to increase the air gap, what happened now? See, I will not change any parameters. I will only increase the air gap. If I increase the air gap, what happened? Let us see. See. So this one is the core. So let us consider this one is the slot. I'm increasing the air gap. You can see, let us consider this is again 10 mm and this is something like 20 mm. Let us consider just for example's sake. And I'm having one conductor here, right? Let us consider it is carrying the current into only. Then in this case, if I want to trace the magnetic flux lines, you can see most of the flux lines will try to take this path. Why? Because when compared to this 10 mm, if they want to travel via the air gap linking with the rotor, they need to take 20 plus 20, 40 mm they need to travel in the air gap. So that 40 mm will make high reluctance path. So they cannot travel through high reluctance path. As such, all the flux lines will try to take this path. One or two will be taking the other way. but maximum flux lines will be taking this path now, like this. So here 1 or 2 will go to the other way, like this, right? So can I say in case of an induction motor, whenever you are increasing the air gap, what happened to the leakages? Leakages will increase. When leakages increases by default, what happened to the mutual flux lines? Mutual flux lines will decrease. When mutual flux lines decreases, the power transfer will also decreases. So can I say like this? With the increase in the air gap, the leakages increases. So if you want to reduce the leakages, the air gap has to be maintained as small as possible, which is enough for the rotor to rotate freely without touching the stator core. So that is the reason in particular induction motor, the air gap length is always as small as possible. So tomorrow if anyone questions you, or I'm having a DC motor, induction motor and synchronous motor, in which motor the air gap will be very small, means you can say blindly it is in induction motor, right? Only in case of induction motor the air gap will be as small as possible. So is my audio audible to all, please? Right, I think there is no strucking, right? So it is free to move, right? Please, done. So I requested you, unless and until is there any problem here, you don't raise the hands, please, right? Please. So can I say with the increase in the air gap, with the increase in the air gap, increase in the air gap, leakages increases, leakage flux lines increases. To reduce the air gap, so to reduce the leakage flux lines, the air gap has to be maintained as small as possible, which is enough for the rotor to rotate freely. That's all. So we have to maintain that one. I think this point is clear. Confirm me, all of you. Raise the hands. Right. Done. Now, one more thing. Not only the air gap. So even the construction of the air gap will also, right? Construction of the air gap will also changes. So the construction of the slot will also changes the leakages, right? What do you mean by it? So you can see this is a complete open slots. See, one more thing, let me remind you, I'm not discussing advantages and disadvantages as of now. Just I'm trying to explain what are leakage flux lines, what are mutual flux lines. So once these concepts are over, then we'll take up that advantages and disadvantages. Next is, I'll take a semi-closed slot. Semi-closed slot. So what is the meaning of semi-closed slot? Means the slot, when it is approaching the air gap, it is partially closed. What does it mean by that? See, so I'll take the core. So this is a semi-closed slot. So you can see when the slot is approaching the air gap, so you can see it is partially closed. Let me consider the same example of 10 centimeter, 2 centimeters like that, right? Fine. So you can see here, so in this a 10 mm path, one flux lines will definitely flow. One 10 mm path, this is a 10 mm path, definitely one flux lines will flow. There is no doubt. But when you are approaching the air gap, you can see this distance is decreased. Let us consider if this is 10 mm, this is 5 mm. Let me consider. So when compared to 10 mm, the 5 mm is offering still low reluctance. If that is the case, you can see this will try to take that 5 mm path like this, like this. Then after that 5 mm, the remaining path is 2 mm, that is crossing the air gap and coming back to that stator again. So that is 2 mm path. So what is the other way? So the remaining flux lines will try to take the 2 mm path like this. So these are called as like this, you can see. So here when the slots are partially closed, the leakages have increased. What is the definition of leakages? The flux lines which are completing the path either with stator core or rotor core. You can see in the previous case how many flux lines are completing the path. Here if I'm talking about only one flux line. But here when the slots are partially closed with the same area, when the slots are partially closed, then you can see two flux lines are completing within the stator. Why? Because so when I'm talking about this length is 10 mm. So previously one flux lines were traveling, definitely one. But as the slots are partially closed, when they are approaching the air gap, the length along that path is reduced. Then one more flux lines will try to flow. Then the remaining flux lines will be taking the other path, right? So can I say in semi-closed slots or partially closed slots, the leakages will be more compared to open slots, right? So the leakages will be more compared to open slots. Is this point clear? Confirm me, all of you. Right. So let me write a note there. In semi-closed slots, in semi-closed slots, closed slots, the leakages are more, leakage flux lines are more, lines are more compared to open slots, compared to open slots, right? So these are some definitions. I'll repeat once again. So what are leakage flux lines and what are mutual flux lines? As I told you that whenever the magnetic flux lines come across more than one reluctance path, the magnetic flux lines will try to divide. It is a basic property of the magnetic flux lines to divide. So here in case of an induction motor, if I take this case, so when the magnetic flux lines are coming from core towards the air gap, then when they are approaching the air gap, they seize two reluctance paths. One is within the stator, they can travel and complete the path. The other one is they can cross the air gap and via the rotor core, again coming back to the stator core, they can complete the path. If you take that example, so if they want to travel via the stator core or the stator slots, what is the length of air they need to travel along that path? 10 mm. Example. If they want to cross the air gap and via the rotor core, if they want to cross complete, so they need to travel 2 mm. How? 1 mm from stator core to rotor core. Again 1 more mm from rotor core to stator core. Altogether, they need to travel 2 mm. So this magnetic flux line find two ways. In along one way 10 mm, along other way 2 mm. So this magnetic flux lines will try to take the 2 mm path. That means they are crossing the air gap via the air gap and they are complete via the rotor core. They are completing the path. So the flux lines which are linking with both the cores, which are passing with both the cores, we are naming it as mutual. The flux lines which are linking with only either stator or rotor, but not both, we call it as leakage flux lines, right? So here it doesn't mean that the mutual flux lines will be always linking. They don't have the, they have love and affection with the rotor. No. As you can see when compared to the slot width, The air gap length is very small. As a result, they are linking with both the pores. But very unfortunate, if I'm trying to increase the air gap, then you can see the leakages have increased compared to the mutual flux lines. So that is the reason, particularly in case of induction motor, the air gap has to be always as small as possible. If you're trying to increase the air gap, definitely the leakages will increase. When leakages increases, the mutual flux content will decrease, the performance of the machine will decrease. So that is the reason, but in particular, this induction motor should be designed for very smaller air gap, which is enough for the rotor to rotate freely. We are not supposed to design with larger air gap. If so, leakages will increase, the performance will come down. Not only with the increase in air gap, the leakages will increase. Even if the air gap is small, when compared to open slots, in semi-open slots, the leakages will be increased. Why? Because you can see when the slots are partially closed, then the reluctance of the path along that slot will be decreased, and one or two flux lines will be passing through that path, and hence the leakages will increase. Now, is this point clear? Is this point clear? Confirm me, all of you. Right. So these are something about the leakage flux lines and mutual flux lines, right? Done. Now let us discuss the advantages and disadvantages of the three types of slots. And after that, we conclude which slots are being used for induction machine. And just right before to that, see, one of the student has texted yesterday, sir, is there any relationship between poles and phases? See, Baba, so each phase is designed for a particular pole. So there is no relation like NS is equal to 120 TF by P. So we don't have any relation. We design poles for a particular phase. Just after this, I'll come to the topic only. You can understand what do you mean by poles, right? Don't worry, right? Now I'll be taking the concept of advantages and disadvantages. First, let me start with open slots. I'll be taking open slots. Open slots. As the name suggests, open slots means the slots are completely open. The slots are completely open. Let me draw a stator core with completely open slots. A part of the stator core I am drawing where you can see the slots are completely open. Completely open. Like this. These are completely open slots. Right? Let me draw a single slot view, which already we have seen. Single slot view. So this is one conductor. Let us consider it is carrying the current like this. So here the leakages will be very less. Mutual flux lines will be more here. Just I am talking with respect to 5 flux lines. You can understand that. See, no textbook will explain all this. Please try to understand. Right, done. Mutual flux lines are more. Now let us go for advantages. After that, let us go for the disadvantages. Right, I'll be talking about advantages first. Advantages. Advantages. What is the first advantage is, as you can see, the complete opening of the slot. The placing of conductors inside the slots is not at all difficult. In other way, the winding procedure with open slots is very simple and easy. Why? Because if you open the machine and if you look into the slots, you can see the complete opening of the slots. As you can see the complete opening of the slot, so placing the windings is not at all difficult. So winding procedure is simple and easy. The first one is the winding procedure is simple and easy. Winding procedure is simple and easy. Why? Because we can see the complete opening of the slot. Simple and easy. Simple and easy. The second one is you can see the leakages are less. When the leakages are less, the mutual flux lines are more. When the mutual flux lines are more, the power transfer to the rotor will be more. When the power is more, the torque which depends on that will be more. So the motor will have very good torque characteristics. The torques will be very high. So the leakage flux lines and leakage reactance are very less, very less. I think for you, I think transformers is finished, right? Raise the hands if transformers is finished, at least for some batches, right? So I think your teacher might have explained you what is the relation we are having between leakages and leakage reactance. I will not be discussing, see some batches may be there, for them it may not be over, one or two, yeah. But I repeat, don't worry. So I know whatever is required, I'll explain, don't worry. Your teacher might have explained you what is the relationship between leakages and leakage reactance. So what is the difference means? See, if you consider a transformer core with infinite permeability, infinite permeability. So when I am having a transformer core with infinite permeability, so if I consider a coil here, so whatever the EMF that is induced in the coil, right, is only due to that mutual flux lines, and this EMF magnitude will be equal to your V, equal to V. But fortunately or unfortunately, if the permeability of the core is not infinite, if it is only finite, then definitely a part of the flux is leaking here. So a part of the flux leaks here, leaks here, leaks here. In that case, this is not equal to that. V is not equal to E1. So here in this winding, so there will be two EMFs. One EMF will be due to that mutual induction, mutual flux. The other one will be due to that leakage flux, leakage flux. So here, whatever the EMF we are having due to that leakages, so we are representing with a equivalent reactance term. Why? Because here V is not equal to E1. So definitely your V should be equal to something into E1. So whatever that EMF magnitude we are having, that we are representing with the equivalent reactance JIXL into I, that drop, and that XL, how we are going to find out means the EMF that is induced due to leakage flux lines by the current. If the leakages are more, if the leakages are more, the EMF induced in the winding due to that leakage flux lines will be more, then the leakage reactance will be more. So what is the relation we are having between leakage reactance and leakage flux means they are directly proportional. More are the leakages, more will be the EMF induced in the winding due to leakage flux, and its equivalent is represented with a leakage reactance drop. So that leakage reactance, how we are going to find out means it is the EMF that is induced in the winding with a leakage flux by the current. If the leakage flux are more, the EMF will be more. When the EMF is more, the leakage reactance will be more. I hope this point is clear. Confirm me all of you. Confirm me all of you. So this your teacher might have explained. If not, in cut short, inductance is nothing but L, reactance is omega L, right? So when L is more, then omega L is also more. Like that also you can remember. So whenever we are talking about more leakages, definitely the leakage reactance will be more. But the correct way to explain what is the relation means, so this will be detailedly discussed in your transformer. So if I take up now, so it will take more than an hour. So not required for us. So only I need a relation. If the leakages are more, the EMF induced in the windings due to that leakage flux lines will be more. And if that EMF is more, the ratio of that EMF by current will be more. The leakage reactance which is represented in series with the line is also more. So what is the relation we are having between leakage flux lines and leakage reactance means directly proportional. So this your teacher might have discussed. If not, for other people, you can see this. So here you can see in open slots, the leakages are more. So leakage flux line and leakage reactance are less. So why? Because the leakage lines are less here. So leakage flux lines will be less here. So these are the advantages of which is slots. open slots, right? Once again, as we can see the complete opening of the slots, the winding procedure is very simple and easy. So we don't find any difficulty in placing the conductors of that particular winding. So that winding procedure will be very simple and easy. The second thing is, as you can see, the air gap length is less when compared to the slot width. So most of the flux lines will be trying to cross the air gap and they are linking with the rotor core and they are coming back. As such, the leakages are less, the mutual flux lines are more. When the leakages are less, the equivalent leakage reactance is also less. When the leakages are less, the power transfer to the rotor will be more, the torques will be more, right? I hope this is clear. Confirm me all of you. Confirm me all of you. Right, done. Now, what are the drawbacks? Drawbacks. So drawbacks. See, Baba, once again, I'm admonishing you. It is an indirect warning also, you can assume. Unless and until you are clear with this concept. So in the coming days, I'm going to talk about the performances. So there I say with open slots, the leakages are less. Again, don't raise a question, sir, why the leakages are less? So please try to understand this. Why the leakages are less, what are leakage flux lines, you please understand, then you can reflect there. Please remember that, right? Next one is disadvantages. Disadvantages. So what are those disadvantages means? You can see here the air gap is non-uniform. Why the air gap is non-uniform? You can see under the slot, so this is called a slot. Under the slot the air gap length is more, and under the teeth the air gap length is less. So something like 50% is occupied with the slots, 50% is occupied with the teeth. So this air gap is non-uniform. So when the air gap is non-uniform, so most of the flux lines will try to take a low reluctance path. So which one is a low reluctance path? The teeth path, like this. So less number or no number will be flowing through the slots. Then you can see the flux distribution is non-uniform. When the flux distribution is non-uniform, the torque which it depends on that is also non-uniform. Then you can see the motor will have noise and vibration, which already I told you yesterday. So whenever I'm talking about noise and vibration, indirectly I'm using one term called as harmonic torques. So the torque is supposed to have a smooth operation. So it is not having a smooth operation means some unwanted torques are overlapping on that and it is making the motor noisy, and we name it as harmonic torques. What is that? We'll see. So can I say here, because of the wide opening of the slots, the area flux distribution is non-uniform. If it is non-uniform, harmonic torques are produced, and these harmonic torques will give rise to noise and vibrations. Is this point clear? Confirm me, all of you. Confirm me, all of you. Right. So I'll write area flux distribution. Area flux distribution is non-uniform, and due to this, harmonic torques are produced, and these harmonic torques gives rise to noise and vibrations. Noise and vibrations. Noise and vibrations, right? I hope this point is clear. Confirm me, all of you. Confirm me, all of you. Right, done. Thank you. So don't feel if I'm asking you to confirm, just it is a indirect communication between you and me. Please understand that, right? The second one I'll tell you, right? See, now I'll consider two magnetic circuits. Please see, I'll consider two magnetic circuit. This is one magnetic circuit with very small area. This is one more magnetic circuit with considerably larger area. Larger area. You can see this is a larger area. So here the number of turns on either side are same. Let us consider the number of turns are same. If I consider for the same flux, in which magnetic circuit the magnetizing current will be more, right? Or which magnetic circuit will draw more magnetizing current? If I'm calling it as A and B, so which one will be drawing more magnetizing current? Means the magnetic circuit B. The reason is the magnetic circuit B, the magnetic circuit B is having more or draw more magnetizing current. The reason is, if you just recall Ohm's law for magnetic circuit, just I is equal to V by R. So flux is equal to MMF by reluctance. As I'm talking for the same flux, so MMF by reluctance should remain constant. Or MMF is directly proportional to reluctance. MMF is N into I mu is directly proportional to reluctance. As you can see, the number of turns are same. So the magnetizing current is directly proportional to reluctance. Then you can see in which magnetic circuit the reluctance will be more, means in the second case. Why? Because these magnetic flux lines, they need to travel more length in air. As a result, the reluctance will be more here. When the reluctance is more here, the magnetizing current drawn will be more here. The reactive power drawn will be more here. As a result, the no load power factor will be less and operating power factors will be less. It is comparatively less, right? So for the same flux, the second magnetizing circuit will draw more magnetizing current, power factors will be less. Is this point clear? Confirm me, all of you. Right, done. The next point here to be discussed is, you can see here, this is the air gap. Generally, what is the air gap in induction motor? General air gap is this. Generally, when I'm talking about air gap, so this is the air gap. Generally, this is the air gap. This is the air gap. Generally, this is the air gap. But you can see the air which is present here, the air which is present here, the air which is present here is adding to the air. So this air gap length, when it is adding to the air gap length, the average length of the air gap will be increased. It looks like the smaller air gap will be increasing. So it is something like in your power system, you might have discussed something about corona. Corona means it is not the pandemic which I'm talking about. What is a corona? If you take a conductor, then under foul condition, when the field intensity is less than 10 kilovolts per centimeter, so the air molecules which are surrounding the conductors will get ionized. So ionize. So that area around the conductor will be acting as a path for carrying current. So that means the surrounding area will be acting as a path to carry the current. As a result, the current can try to flow through that path. So in this case, what is the effective area of the conductor? Increases. The true area is small, but the effective area will try to increase. So I'm trying to talk about the virtual area. So the virtual area, if anyone sees with the naked eyes, I just imagine seeing the naked eyes. So it looks like the current is flowing even the outside the conductor. Why? Because the path is conducting. So I can see the virtual area of the conductor is increased. Is this point clear? Confirm me. Right. So here also the air gap is small only. The air gap is small only. You can see the air gap is small only. Here the air gap is small only. But because of the air which is present here, the air which is present here is adding to the air gap. As a result, what happened to that effective length of the air gap increase? It looks like the air gap is this much. Why? Because the air is that air which is present in the slot is adding up. So air gap is increased. When the air gap is increased, the magnetic circuit which is supposed to be A Right. So there is some technical issues. I'm back with that. Don't worry. Right. Can you see the board now, all of you? Confirm me once. Right. Thank you for your patience. Thank you. See, so because of the wide opening of the slots, what happened now? So the average length of the air gap will increase. So the magnetic circuit, which is supposed to be A, it looks like B. Then what happened? The electric increases, magnetizing current will increase. Then obviously the machine will draw. So is everything clear? So my voice and other things are clear. Just once again confirm me, raise the hands. Videos, everything is clear. Yes, thank you. Right. So the second one is the average length of the air gap will increase. As a result, reluctance will increase. The magnetizing current is increased, right? Magnetizing current is increased. The power factors will decrease. The second problem is, the second drawback is, due to the wide opening of the slots, due to the wide opening of the slots, opening of the slots, of the slots, the average length of the air gap is increased, is increased. Hence, machine draws more magnetizing current. As a result, the power factors at no load and at full load are very less. Very less. So this is something about the second drawback, right? So once again, on one side of the coin, we have advantages. On the other side of the coin, we have the disadvantages. What are the advantages we have? As you can see, the complete opening of the slots, the winding procedure is simple and easy. The leakages and the leakage flux lines are very, very less. The drawback is, as you can see, the air gap is non-uniform. The flux distribution is non-uniform, and hence the harmonic torques are produced, and these harmonic torques will give rise to noise and vibration. The second thing is, due to the wide opening of the slots, the average length of the air gap is increased. Hence, the reluctance increases, thereby the power factors will be reduced. Is it clear? Confirm me once, all of you. Raise the hands. Right. So this is something about the open slots. Now let us go for the semi-open slots or semi-closed slots. The second category is semi-open slots. Semi-open slots or semi-closed slots. Now let me draw a stator with the semi-closed slots, right? Let me draw a part of the stator core with semi-closed slots. You can see. So these are semi-closed slots, roughly. Semi-closed slots. This is the stator core with a semi-closed slots, right? Let me draw a single slot view. This is a single slot view, right? Then already we have discussed the leakages here. Leakages will be comparatively more here. These are the mutual flux lines. right? Done. Now let us first discuss the drawbacks. After that, we'll discuss the advantages of these semi-closed slots. Drawbacks or the disadvantages. See, one request, due to this power issues, sometimes suddenly this network may be disconnected. So don't get be like worried. So I'll try to rectify, right? So just wait for 5-10 minutes or 5-10 minutes up to like that. Still, if you're not able to have this reconnection, then you can call to the host, which you have, I mean, number you're having, you can call, right? But just hold. If anything is happening for more than 5 to 10 minutes, then I'll call to them. But just don't worry, just 5-10 minutes, hold, right? Please. Disadvantages, right? So what is the first disadvantage means? You can see these advantages and disadvantages are not by their own, they're compared to open slots. So in open slots, the winding procedure is very simple and easy. But here, as you can see, the slots are partially closed. The winding procedure is not that much easy, so comparatively it is difficult. So in open slots, the winding procedure is very simple, but here it is difficult, but not complicated. So here winding procedure is difficult, but not complicated. Difficult. Second point is you can see the leakages are more here. You can see the leakages are more, and hence the leakage reactance is also more. So when the leakages are more, the power transfer to the rotor will be less. Leakage flux and hence and leakage reactance are more compared to open slots. Compared to open slots. Compared to open slots. Right? These are the drawbacks. Right? Please confirm me this. Right. Then what are the advantages we are having? Advantages. So let us see the advantages. First advantage is, see, in open slots, let me see. Let me explain. See, we are trying to discuss everything in detail. If I'm taking in open slots like this, you can see the air gap is non-uniform. So under the teeth, the reluctance is less. When the reluctance is less, more number of flux lines will be passing under the teeth like this. Under the teeth like this. And you can see there are no flux lines passing through the slots. Why? Because air gap is too large. The vertical length is too large. Is it clear? Confirm me. Is it clear? Confirm me. Right. But when I'm talking about the semi-closed slots, you can see semi-closed slots. Like this. Like this. Then if you can see here, all of you, I'm zooming it, you can see here, the magnetic flux lines are traveling like this. There is no doubt in this. Definitely there is no doubt in this. But you can see as the slots are partially closed, so when compared to this length, this length, this length of the air gap is less. That means on the sides of the slots, as they are partially closed, the length of the air gap is reduced there. You can see here, this is the air length and this is the air length. You can see on the edges, the air gap length is reduced. Then as a result, the flux lines will try to flow along this path also. On the edges, the flux lines will try to flow also like this. So there will not be any flux lines flowing on the center. You can see here, you can see like this. So you can see here, is there any flux line? In the first case, can you see, is there any flux lines passing through the slots? No. But in the second case, one or two flux lines are passing through the slots. Then I can say the flux lines are little bit scattered even in the slots. It looks like the flux lines are uniformly distributed. When the flux lines are uniformly distributed, what happened to that harmonics? The harmonics are going to be minimized, they are going to be reduced, and noise and vibrations are going to be reduced. So this is one of the advantages what we are having with semi-closed slots compared to open slots. Can I say, as the slots are partially closed, then you can see the flux lines are uniformly distributed. Even they are coming in the slot region also. As a result, the flux distribution will be uniform, merely uniform. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. Can I give the note here? What is that? So the first advantage is the area of flux distribution. The area of flux distribution is merely uniform, and hence harmonic torques are reduced. Harmonic torques are reduced. I hope this point is clear. All of you confirm me once. Confirm me once if it is clear. Right. This is first advantage. What is the second advantage we are having means, second advantage, as the slots are partially closed, if you take corona means not this one. So if this ionization is not maximum, say only partial ionization, then if you can see only a part of the area will be occupied. If the ionization process is more, then you can see the surrounding area will be increased. So here also in case of semi-closed, as the slots are partially closed, some of the air content is reduced. Why? Because it is partially closed, it is occupied with the core. You can see here, this is the air part, but here it is a core part. Then you can see the amount of air in the total length is reduced. When the air content is reduced, what happened to that average length of the area? Reduces. When average length reduces, what happened to the reluctance? Decreases. The power factors will be improved. That means when compared to the open slots, the power factors will be more, right? So can I say the average length of the air gap is reduced? Air gap is reduced. Hence, the power factors are improved. I'm writing directly. I'm not writing reluctance and other thing. Power factors are improved at no load and full load. No load and full load. Is it clear? Confirm me all of you. Confirm me all of you. Is it clear? Right. So these are the advantages and disadvantages of which is slots, semi-closed slot. But please keep one thing in mind. These are not like individual advantages and disadvantages, but they are when compared to open slots. These are the advantages and disadvantages. They are not individual. The last category is the closed slots. The last category of the slots is closed slots. Let us go for closed slots. Closed slots. Let me draw the stator core with the closed slots. Closed slots. You can see closed slots. Let me draw a single slot view. Like this. So here if I'm trying to draw the leakages, you can see this is the core. Whereas it is a core, then most of the flux lines will try to take that core only instead of traveling the air gap and coming back. So one or two flux lines will be taking the other path. See, no flux lines will get overlap. Please understand that. You can see here, as the slot is inside, so the core is there to complete the path. So most of the flux lines will be completing the path within the core itself. So in this case, the leakages are very, very high. So more leakages will be there in closed slots. So if I'm trying to draw the stator with this, you can see if it is a stator core, I'm trying to draw the side view. Side view. This is the side view. So let us discuss the drawbacks first. Then after that, we can go for the advantages. What are the drawbacks? See, what are the drawbacks? The first one is the winding procedure is complicated. Here, we cannot see the slots from inside the core, but if you stand next to the core, then you can see the slots are available inside the core. We cannot see the slots from inside the core. If you open the machine, you cannot see the slots from inside. But when you come next to the machine, then you can see the slots are available. So here, what is the winding procedure means? You take the conductor, place it in one slot, go to the other side, take it out. Like that, conductor to conductor, like that you have to place the conductors like this. So here the winding procedure is complicated. But whereas in case of open slots, it is easy. In case of semi-closed slots, it is difficult, but here it is complicated. Why? Because we cannot see the slots from inside. We can see the slots only from side. Is it clear? Confirm me. Is it clear? Confirm me. Right. So can I say the winding process or winding procedure is complicated. Second thing is you can see the leakages are more, leakage reactants are more. Leakages and leakage reactants are very high, are high. These are the drawbacks. Then what are the advantages we are having? Advantages we are having means you can see here air gap is uniform. You can see here air gap is uniform from this end to this end. The air gap is uniform. When the air gap is uniform, the flux distribution will be uniform. When flux distribution is uniform, harmonic torques are almost absent. When the harmonic torques are almost absent, the machine will have a smooth and quiet, calm operation. So there will not be any noise, there will not be any vibration. So in which case, the machine will have very less harmonic torque means in case of closed slots. Is it clear? Confirming? Confirming? Right. So uniform air gap, uniform air gap, flux distribution, and hence harmonic torques are almost absent. Harmonic torques are almost absent. Then you can see the second one is, so there is no additional air. So here there is no additional air added to the air gap. But here if you can see, this air is added here, this air is added here, but there is no additional air added to this. So this is the core, but here there is no additional air. So the air gap is very, very less. When the air gap is very, very less, reluctance will be less, magnetizing current will be less, and hence the power factors will be very high, right? Smaller area, hence the power factors at no load and running are high. Running are high. Are high. So this is something about your flows. So can I say on one side of the coin, the drawbacks. What are those drawbacks? Winding procedure is complicated. The leakages are very high. On the other side, the flux distribution will be uniform, no harmonic torque. The air gap is very less, very good power factors, right? Is it clear? Confirm. Is it clear? Confirm. So you can see here, if I mix up all these things, all these slots, we have mixed advantages and disadvantages. In case of open slots, the winding procedure is easy, but here it is complicated. Like that, we are having mixed advantages and disadvantages. So that is the reason, before I conclude which slots are being used for induction motor, I go for a tabular comparison. So basing on the tabular comparison, we will decide which slots are being used for induction machine. Let us go for a tabular comparison. So I'll start with open slots, semi-open slots, then closed slots. So let me first discuss with respect to magnetizing current. So in which case the magnetizing current will be more, means here you can see the magnetizing current in open slots will be more compared to the semi-open compared to close. Why the magnetizing current will be more, means the average length of the air gap is more, reluctance is more, magnetizing current is more, power factors will be less. So in which case the magnetizing current is more in open slots. But here in closed slots, you can see the air gap is very small. If the magnetizing current is more, the no load power factor will be less compared to this, When the no load power factor is less, the operating power factor is also less. We'll see that, don't worry. Right. Next one is, what happened to leakages here? In open slot, the leakages are very, very less. So can I say the leakages and the leakage reactance in open slots is less compared to semi-open compared to close. Already we have discussed all this, you can see. And in which case the harmonic content is more in open slots, as that air gap is non-uniform, harmonic torques are more. Then if you see this comparison table, you can see the semi-closed slots are having the advantages of open and the advantages of closed. So that is the reason in most of the induction machine, which type of slots we use, means we use semi-open slots. So tomorrow, if anyone questions you, Are Baba, can you please support why semi-closed slots are used in induction motor, means you have to list out these advantages and disadvantages. Finally, you have to conclude that on this, we can say the semi-closed slots are used in induction motors. Is this point clear? Confirm me. Right. So can I write note here? The semi-closed slots, are having the partial advantages of, one second. Yeah, the partial advantages of open slots and closed slots. As such, in most of the induction machines, most means, what is the range means? It is 5 to 50 HP. 5 to 50 HP roughly. Semi-closed slots, are used. Is this clear? Confirm all of you. Right. But when I'm talking about low HP motors, less than 5 HP, so which slots are used means we use closed slots. Now the question comes, sir, why for low HP motors we use closed slots? As of now, one of the major reason is so to eliminate the need of starters. So we are going to see in the coming days, even though a three-phase induction motor is a self-starting motor, we need a starter. That starter is not for starting the motor or twisting the motor, but to limit the high starting currents. Now we are going to see, particularly in case of starting methods, a separate topic for 4 to 5 hours. There we'll see why we need a starter there. So if I start a motor with a three-phase induction motor without a starter, and then there is a possibility that the windings may get damaged. So compulsorily, so a three-phase induction motor has to be started with a starter, right? But when I'm talking about low HP motor, the cost matters more. For example, say the cost of a less than 5 HP motor is at 10,000, some 10,000. But if I'm using a starter to control the current, the cost of a starter is also some 5,000. So what is the total cost? It becomes 15,000. So because of this starter, the overall cost of the machine is increased. So if I found some reason, or if I find some way, if I eliminate the need of starter, then what will be the overall cost? The overall cost of the machine will be reduced. So in order to eliminate the need of starter for low HP motors, we use the so-called as closed slots. Then you may have a doubt, sir, how come, sir, the closed slots can reduce the starting currents or eliminate the need of starter? See, if I am approximating the starting current as of now, it is the voltage by the reactance, impede resistance plus reactance. Just now in the comparison, you have seen that which slots are having more leakage reactance means the closed slots have more leakage reactance compared to the other. So here, if I'm using closed slots, the leakage reactance compared to other slots will be more, but because the leakages are more. When the leakage reactance is more, definitely the starting current drawn will be less. So the starting current will be less. So that is the reason we use closed slots for low HP motor to limit or to eliminate the high starting currents, right? That is starter. To eliminate that starter, we are using this closed slots. Then indirectly, sir, with the closed slots, what is the relation we are having to eliminate the starter? The reason is why we are using starter means to reduce the starting current, right? Why the starting currents are high, we'll see later, to reduce the starting current. So if I'm using closed slot, what will be the leakage reactance? The leakage reactance is high and hence the starting current will be less. But what is the main difficulty we are having with these closed slots? The winding procedure is very difficult. So, but as it is a low HP motor, the size will be like manageable and you can sit with the machine. Even if it is difficult, you can wind the or we can go for the winding without any difficulty. Even if it is complicated, you can sit and you coolly can go for the winding, right? Is this point clear? Is this point clear? Right. So can I say for low HP motors, once again, for low HP motors, which type of slots we are using means we are using closed slots. Why we are using closed slots means to eliminate the need of starters. So what is the role of this closed slot means compared to the other slots, the leakage reactance will be high and hence the starting current will be less if I'm using the closed slots. But what is the main problem we are having means the winding. So it can be managed, right? So here for low HP motors, for low HP motors, less than 5 HP, closed slots are used to eliminate the need of starters. The need of starters, right? Starters, starters, right? So for low HP motors, which one is which slots are using means closed slots. But when I'm talking about for high HP motors, more than 50 HP, open slots are used. Open slots are used. Open slots are used. What is the reason for that? See, I'll tell you one thing. Say you are sitting in a room, all doors and windows are closed. There is no AC working, all the doors and windows are closed. Can you feel the external air? No. Say on the other side, on the opposite side of the room, heavy wind blow is there. Wind blow is there, heavy wind blow is there. But as all the doors have been closed, you cannot feel that wind. Still you feel suffocated. Is this point clear? Is this point clear? But when I open the doors, then you can see that wind will be coming inside, that air will be coming inside, and you can feel some cooling effect, some chilling effect. Is it clear? Is it clear? Right. So here also, when I'm talking about high HP motors, so when an high HP motors means the currents will be very high. When currents are very high, the ohmic losses will be very high. When the ohmic losses are very high, the temperatures will be very high. Then if the slots are completely open, here this is the rotor which will be rotating in the area. This is rotating. When the rotor is rotating, the air will be in motion, and that air will be hitting the conductors. That air will be hitting the conductors. As a result, the temperature of the conductor is reduced. Why? Because the slots are completely open, and you can see this rotor will be rotating with very high speeds. Then there is a wind effect which is trying to reduce the temperature. But if the slots are completely close, then this is a conductor. The ohmic losses will be more, the temperature will be more, but there is no direct contact between the air. Even air is here, so this air is not hitting the conductor, and hence it looks like that conductor is locked within the room, and there is no cooling effect, and hence there are chances are there the windings will get damaged. So for that we are using which is slots? Open slots. But with open slots, you can see the power factors will be very poor, right? Already we have seen. So we are using some capacitor bank. Why? Because high HP motors are used in industries. So to compensate that, we'll be using some capacitor banks like that, right? So this is something about the slots. Confirm me if it is clear, all of you. All right. So tomorrow, if anyone questions you, Array, which slots are used for induction motor? Then you have to question, what is the range? Medium range, semi-closed. Low HP, close. High HP, open. Why? You have to list out all these things, right? So this is something about your slots. The next and very, very important concept is the formation of poles. Formation of poles. This is a very, very important concept. One has to understand formation of poles. Formation of poles. Very, very important concept. See, yesterday, when I was trying to explain you the concept of electrical angle and mechanical angle, the angle which we see is with eyes, naked eyes, we call it as mechanical, which we cannot see with the naked eyes. In cut short, we call it as electrical. But we can imagine if it is a 4-pole machine, the electrical angle will be 720. If it is a 2-pole machine, the electrical angle will be 360. Why? Because north to south is 180, south to north is 180. Like that, you can decide, right? So here also, in case of your DC motor, you can see to the yoke, we fix the poles. We fix the poles. Then I can say by looking into that machine, okay, in the yoke there are 2 poles. It is a 2-pole yoke. They are called as heteropolar machines. Why? Because we can see the poles are projected out. But whereas in case of induction machine, so there are no projection of the poles, but the poles will be continuously rotating inside. So these are called as homopolar. The poles which are not seen outside are called as homopolar, right? I think in your DC, you are going to discuss all these things. No need to worry. So what is the meaning of concept of pole formation? So this is a very, very important concept. Listen, all of you. So during my starting classes, so I made a very clear statement that if you want to have torque, the turning effect, the twisting effect, then you should need how many magnetic fields? 2 magnetic fields. And one more statement I'm adding. The relative speed between the two magnetic fields has to be zero. Then only there will be a continuous rotation or there will be a continuous torque, right? So I'm just giving a generalized statement. So for the production of torque, the turning effect, there has to be two magnetic fields and the relative speed between the two magnetic fields has to be zero. Now we are going to find out the answer for all these things, right? So if anyone knows, so it is waste of time if I ask, right? Now I'm trying to answer to this question, right? So anyone knows, just if anyone knows, please answer. My question is why we need two magnetic fields and why the relative speed between the two magnetic fields has to be zero. If anyone knows, please try to answer. See, Sunanda, sir, it is semi-closed or semi-open. We can use any name, no issue. To reach synchronism, no. Continuous attraction and repulsion, good. But how? So here there is no magnetic lock in induction, but in transfer, in synchronous it is, correct. Right, enough, please stop. So I'll explain. So please stop, no need to text, please stop. Right. So we are trying to look in general how the rotor or how the rotating part of a induction machine will rotate. So I'm trying to explain the concept of pole formation. So please stop, don't text. So first what I'll try to do means, first I'll try to take up the DC machine, and with respect to DC machine, I'll try to explain. So DC motor. So if you understood this DC motor, how it rotates, then you can answer to this other questions, right? First, let me start with DC motor. Formation of poles in DC motor. But it doesn't mean that I'm discussing DC motors. So after this concept is over, you are supposed to answer to these questions. What are those questions? Why we need two magnetic fields? Why the relative speed between the two magnetic fields should be zero? Then why the stator poles and the rotor poles should be equal? So these three questions you should answer. Once again, why we need two magnetic fields? Why the relative speed between the two magnetic fields should be zero? Why for the production of torque the pole should be same, right? We are supposed to answer to these three questions. So if I want to explain the concept of this pole formation, then you should know some basics. What are those basics? Please understand this. So if I consider a bar magnet, say it is a north pole, so this is a south pole. If I consider a bar magnet, and you know that with respect to a bar magnet, the magnetic field lines will be originating from a north pole and they will be terminating at a south pole. So like this, the magnetic field lines will try to travel. So like this, they are traveling from north pole and they are entering at a south pole. I'm not drawing the complete closed path, you understand. But to complete the path, the same magnetic flux lines will try to travel from south to north internally. South to north internally, right? Done. See, if I just closed this path, if I closed this pole, let me assume that the pole is closed. Then by looking the side, you can see the magnetic field lines are coming out. So this is the core. The magnetic field lines are coming out. Magnetic field lines are coming out. When the magnetic field lines are coming out, then what is the pole that can be imagined there? So you can imagine a north pole. Why? Because you know that if I'm considering a permanent magnet, so with respect to a permanent magnet, the magnetic flux lines will come out from a north pole. If the magnetic field lines are coming out from a north pole, then if I consider a core, and even from the core, if the magnetic field lines are coming out, means what is the pole that can be imagined there means a north pole. So please remember, if you're trying to draw the magnetic flux lines, and if you see that if those magnetic flux lines are coming out of a core, then compulsorily you have to imagine that there exists a north pole there. Why? Because when now we talk about magnetic field, so that is only because of poles. So when the magnetic field lines are coming out of a core, then you have to imagine that there exists a north pole. Because of that north pole, the magnetic field lines are coming out. So can I write a note? If the magnetic field lines are coming out from a core, then imagine there exists a north pole. North pole. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. What happened? Only few are raising the hands. Please try to raise all of you. I can see some 300 plus here, 360 plus here. Right. So you can see the magnetic field lines are entering here. If the magnetic field lines are entering, from which pole they will be entering? They are entering from a south pole. So here the magnetic field lines are entering. Magnetic field lines are entering. So if the magnetic field lines are entering, so from which pole they are entering? South pole. So can I say, if the magnetic field lines are entering the core, then imagine there exists a south pole. So these are some thumb rules which you need to follow, right? So first you need to draw the magnetic flux lines, and after that you need to decide which is a north pole and which is a south pole. You know, previously in IISc Bengaluru, so an electrical engineer is asked to draw the directions of the flux lines. Nowadays we are having many softwares like ANSYS, Informatica, something like that. But in previous days, so they are supposed to draw the magnetic flux lines. So for that, they should understand many things. If you clearly understood how to draw the magnetic flux lines or how to trace the magnetic flux lines, so 50% of your engineering is done. So that much importance we have to draw the magnetic flux lines. Why? Because even it may be a motor or even it may be a generator, so they works only on magnetism, magnetic fields only. So you should know the tracing of that magnetic flux lines, which is a very, very important thing, right? So first point is, if you want to identify what is a pole existing, means you have to identify the direction of flux lines. If the direction of flux lines are from the core, coming out of the core, then you have to imagine that there is a north pole. And if the magnetic flux lines are into the core, you have to imagine that there is a south pole, right? You have to imagine like that. Done. The second point is the right hand thumb rule. So I'm not going to take up that right hand thumb rule. So already you know right hand thumb rule. So what is that right hand thumb rule? If I'm having a conductor, assume that this is a conductor and this conductor is carrying a current, and I want to know the direction of flux lines, then you have to place the thumb of your right hand in the direction of current, then the remaining four curl fingers will give the direction of flux lines. The other one is, if I'm having a coil, then if you want to know the direction of flux lines, then you have to place your four fingers in the direction of current through a coil, then your thumb gives the direction of flux lines. I hope you are clear with this terminology. Please confirm me. Please confirm me. Right. So these things are required to understand the concept of pole formation, right? So now let us see what is the true reason the armature of a DC motor rotates. So if you just hold and if you sit patiently and if you understand clearly, then you can see on the board your DC motor armature will be rotating, just rotating in the sense. So I'll try to explain that like that. Please understand. So here first what I'm trying to do means I'm trying to take a yoke. This is the yoke. To this yoke, I'll be fixing the poles. I'll be fixing the poles. So let us consider it is a two-pole yoke. I'm fixing the poles like this, right? Now what I'll try to do means I have to place the windings. So how many poles are there? Two poles. So for that what I'll do means I'll consider a coil with N turns. How many turns? N turns. So here how many poles are there? Two poles are there. So what I'll try to do means I'll try to split that coil into two parts. Two parts. So this is one part and this is one part. So how many turns per part? N by 2, N by 2. Is it clear? For example, if I'm having four poles, then how many equal parts I need to make? Four. Then how many turns we need to have on each part? N by 4. Like that, if I'm having P poles, then how many parts I need to make? P parts. And how many turns per part? It is N by P. Is it clear? Is it clear? Confirming, raise hands. Right. So what I'll try to do means I'll take the first half and I'll place it here. And I'll take the second part and I'll place it here. I'll place it here. And these two are connected in series. And to that series combination, I'm trying to give a DC. I'm trying to give a DC. What is the meaning of DC? Means with respect to time, the magnitude of that current is same, constant, and there is no alternating nature. So with respect to time, the magnitude will remain same and the flow of current will be always unidirectional like this. Let us consider the flow of current in this upper half of the coil is like this and the lower half of the coil is like this. So this is the area. This is the area. Right? Now what I want to do means this is a yoke. So in the yoke, you can see the dipoles are molecular magnets. Already you have discussed. So when there is no magnetism, all those dipoles will be randomly oriented. But whenever I try to pass a current through the coil which is placed on that, so all the dipoles will try to align. Now, whenever we try to pass a current through that coil, then all the dipoles will try to align. In which direction they try to align means for that I'll be calling upon the right hand thumb rule. So if we just apply the right hand thumb rule on the upper side, you can see the four fingers I'm placing in the along the direction of the current. Then we can see with respect to the upper pole, the magnetic field lines are coming out. They are coming out. So from this, the magnetic field lines are coming out. The magnetic field lines are coming out. Like this, the magnetic field lines are coming out. Will agree with me? Will agree with me? Please confirm me. Why? Because which rule I'm applying? Right hand thumb rule. The magnetic field lines are coming out. Then if I apply the same logic here, if I apply the same logic here to the bottom pole, so even the magnetic field lines are entering. So they are entering like this. So whenever we are having magnetic flux lines, then you have to imagine that those magnetic flux lines are only because of poles, only because of poles. Then I need to decide what is the pole that is formed here, what is the pole that is formed here. Then if I want to decide what is the pole that is formed here, then I have to go back to this logic. What is that logic? If the magnetic field lines are coming out of the core, out from a core, coming out from a core, then you have to imagine that there is a north pole. Why? Because you know that with respect to a permanent magnet, the magnetic field lines will always come out from a north pole or come out from core into air. So here the magnetic field lines are coming out, means what is the pole that can be imagined here? I can imagine a north pole here. Why? Because the magnetic field lines are coming from core into air. So core into air, into air is which pole? North pole. Similarly, if I consider the bottom one, the magnetic field lines are coming from air into core. So air into core means what is the pole that can be imagined there? It is a south pole. Like this, we can form north and south pole. But can we see that north and south pole with our naked eyes? No. But how can we imagine? Means basing on the direction of current and by applying the thumb rule, I can decide the upper one is a north pole and the bottom one is a south pole. Is this point clear? Confirm me. Is this point clear? Confirm me, all of you. Yes. Now the question comes, these are electromagnetic poles or induced poles? I think in my starting classes, I told you, induced poles means if I'm having a core and through that core, if I try to bring a magnet, so this magnetic pole will try to induce an opposite pole. So those are called as induced poles. The best example is in your school days, when you're trying to bring a magnet closer to some iron filling, so those iron fillings will act as a magnet. So those formation, we call it as induced poles. But in the other case, if I'm not having any magnet, but if I'm producing it with the help of a current carrying coil, so we call it as a electromagnet. So any problem? Is my voice clear? So most of you are raising the hands. Is my voice clear? Raise the hands. Right. Now once again, is my voice clear? Is my voice clear? Raise the hands, all of you. So it is not clear. Something. Just let me check. Just 2 minutes. Now it is clear. Now it is clear. Raise the hands, all of you. Right. Done. Now you can see there is no lagging also. So it is clearly going. Done. Fine. Now we are back into the subject again. So you can see from the upper pole, the magnetic field lines are coming down, are coming out, and from the lower pole, the magnetic field lines are entering into the core. Then I can say the top one is a north pole and the bottom one is a south pole. So these are electromagnets or these are induced poles. I told you already. So the formation of poles can be done by two ways. One is bring a magnet closer to a magnetic material, then poles will be induced. The other possibility is place a coil on the core and pass a current through that, the poles will be induced or the poles will be formed. So in this case, we are not bringing any magnet closer to that core, but what is that we are trying to do means we are trying to place a coil, and through that coil we are passing a current. So these poles we call it as electromagnetic poles, and we have the control over this magnetic field. How means by wearing this DC or by connecting a rheostat in series with that, so we can control the field current and we can control the magnetic field strength. So it is a control magnet. So this is a electromagnet or this is a induced pole. It is a electromagnet. Electromagnet. Is it clear? Confirm me, all of you. Is it clear? Confirm me. Right. So I told you that for the production of torque, how many magnetic fields are required? Two magnetic fields are required. Two magnetic fields are required. Now we are successful. We are successful in producing one magnetic field. So this is one magnetic field, or it is one field produced by the field windings and produced by the field current. So we are successful in producing one field. So generally we represent this field as phi m and we are naming it as main field. Main field. That's it. Right? Done. But only one field is not enough to make the rotor to rotate or the armature to rotate. We need one more field. Then only that so called as the rotating part will try to rotate. So how to produce the secondary field or the field number 2 in case of a DC motor? Let us see. So the secondary field is also a electromagnet here. How? Let us see. See, I'll try to draw this field again, but I'm not trying to draw all that story again. Windings and other things I'll not draw. So this is a North Pole. So this is a South Pole. I'm not drawing any lines and other things. You please understand that. South Pole. And I'm trying to draw a armature in between. So I'm trying to draw a armature in between. Right, this is an armature. Just I'm trying to draw an armature. And you know that even armature core is also made up of a magnetic material, your steel. And on the core, we make slots. And in the slots, we place conductors. We place conductors like this. Conductors means not circular conductors. So conductors means they are inside. Then if I see what is the symbol, I can see it is a circle which is seen outside. Please understand that. Like this. And the two ends of those conductors are brought out with the help of a commutator and brush arrangements like this. I'm not drawing all the things, just roughly I'm trying to draw commutator and brush arrangements. And even to this armature winding, we are trying to pass one more DC. So see, I'm not drawing windings like this here. That is understood. Every time I cannot draw that. Please understand. I'm passing one more current to that armature winding, right? So here in this case, the direction of current will be like this. The direction of current can be like this. So one half of the armature windings may carry cross like this. The other half may carry dot like this. This is one possibility. The other possibility is this side will carry dot and the other side will carry cross. So these are the two possibilities. Only these are the two possibilities which will exist in case of your armature winding. So in this case, I'm taking that with respect to me, left hand side are carrying the cross, right hand side are carrying the dot. Cross means into, dot means outwards. If not, opposite will happen, right? Is it clear? Confirm me. Is it clear? Confirm me. Right. Now, if anyone questions, or who is responsible for this field poles? Field poles means I can say the field windings and the field current. If that is the case, even in the armature also, we are having armature windings and we are passing current. So because of that, there is one more flux. Yes. So can you please plot that? Yes. Again, which rule I'll be applying? Right hand thumb rule. I'll be applying right hand thumb rule. So if I'm trying to apply right hand thumb rule, what will be the direction of flux lines here? You can see clockwise like this. These are individual flux loops. Is it clear? Confirm me. Is it clear? Right. Now I need to draw the resultant. So if I want to draw the resultant, what I'll do means I'll consider the conductors which are side by side. So I'll be calling this one as conductor 1. I'll be calling this one as conductor 2. I'll be taking two conductors which are side by side. Please see. So this is one conductor 1 and this is one conductor 2. So it is cross. It is cross. What is the direction of flux lines? Clockwise. So here it is also clockwise. Then if you can see between the conductors, you can see the flux lines are in opposite direction. So these flux lines will get cancelled. Why? Because they are in opposite direction. Then what will be the resultant of these two? Means the resultant of these two will be like this, like this, like this. So don't draw like this. If you draw like this, so that will be longer length. So no flux lines will try to take a longer length. So this is wrong. So you have to draw a straight line. You have to draw a straight line. Is it clear? Is it clear? So can I say if two conductors, if they are carrying the currents in same direction, and if the magnitudes of currents are same, then there will not be any flux lines passing through those two conductors. Why? Because so those flux lines between those two conductors will get cancelled out. So there will not be any flux line. So what will be the resultant of all these individual flux lines? So the resultant will be like this. Resultant will be like this. Like this. Is this clear? Confirm. Is it clear? Confirm. Now, if I apply the same thing even for the left hand side, even if I apply the same thing for the left hand side, you can see the magnetic flux lines are like this. Then what is the resultant of all this? The resultant of all this will be like this. Like this. Like this. I hope you understood this. Finally, once again confirm. I think this is clear. Right. Now you please tell, this is air and this is core. This is core. Now the magnetic field lines are entering from air into core, air into core, air into core. If the magnetic field lines are entering from air into core, what is the pole that can be imagined here? A south pole can be imagined here. And the magnetic field lines are entering from core into air. So core into air means what is the pole that can be imagined here? A north pole can be imagined here. Like this, we can have one more magnetic pole pair in the armature circuit. Again, this magnetic pole pair is also an electromagnet. Why? Because on the armature core, we are rounding or we are wounding a coil, and through that coil, we are passing a current. So because of that current which is flowing through the coil, will set up an MMF. That MMF will try to align all the dipoles inside, and hence that core will act as a magnet, a cylindrical magnet. You can say this is a one more magnet. Again, this is an electromagnet, right? Is it clear? Confirm. Right. Now you please see. Now we'll please see. See, I consider one conductor here and I name it as A. I'll name it as this one as A. A. And on the other side, I'll consider one more conductor and name it as a B. B. Now assume that this armature is rotating. Assume that this armature is rotating. When this armature is rotating, you can see this conductor will come here. It will touch the commutator. Again, after that, it will come here. So the position of this conductor will change from south pole to north pole. After that, after touching that commutator, it will come here. Then when it is coming here, what will be the direction of current in that conductor? It will be converted into cross. So here when it is carrying dot, but once the armature moves, when the position of this conductor changes after touching the brushes, so it is converted into cross. So who is doing the role of changing the direction of current in a particular conductor when it is touching with the brushes or commutator means the commutator. So the role of the commutator is to change the direction of current in a particular conductor which is undergoing short circuit with the brushes. So once this armature is moving, so this conductor will move, it will come and touch brush. Again, after that, it will come to the other side. So when it is coming to the other side, so the direction of current will be reversed. From dot, it is going to convert it into cross. This point clear? Right. Similarly, when one conductor is coming from that side to this side, so one more conductor will be coming from this side to that side. Then in that case also, what will be the direction of current? So that is converted into cross into dot. So who is doing the role of that means a commutator. So can I finally conclude, irrespective of the speed, irrespective of the speed, in this case, the conductors which are under the south pole will carry dot, and the conductors which are under the north pole will carry cross. But when that armature is moving, when the positions of the conductors are changing, still the direction of current is maintained as a cross in south pole and north pole and dot in a south pole with the help of a commutator. Is it clear? Confirm me. Right, done. So now how many electromagnets are there? How many magnetic fields are there? You can see there are two magnetic fields. So the first answer is over. So for the production of torque, how many magnetic fields are required? Two magnetic fields are required. You can see two magnetic fields here. One is the field, the other one is the armature magnetic field. So we represent this one as an armature flux. I think in your DC machine, your teacher might have explained you called as armature flux. But I'm talking this one as a field due to the armature windings and armature current. It is a armature field, right? How many magnetic fields are there? Two magnetic fields are there. Then after that, I'll apply the simple magnetism properties. What is that? Like poles repel, unlike poles will attract. You know that. Like poles repel, like poles repel, unlike poles attract. Poles attract. You know that. Attract. You know that, right? Now you please tell me. So as soon as the south pole is formed here, then immediately it sees a north pole in the yoke. So what exists between the south pole and north pole? Attraction. Similarly, this north pole sees a north pole here. What exists between these two? Repulsion. Again, between this north and south, what we can see? Attraction. So between south and south, what is that? You can see a repulsion. So can I say the poles which are formed in the armature, they seize an opposite poles in the field. Because of these opposite poles, there is an attractive force, repulsive force, attractive force, and repulsive force. And you can see all these attractive and repulsive force are acting in only one direction. And hence, the armature will try to rotate. The armature will try to twist. The armature will try to turn. So twisting effect, turning effect is nothing but torque. The motor will try to produce a torque. Now the armature is rotating. The armature is rotating. What is the reason to rotate? Means to align this south pole with this north pole and this north pole with this south pole. So to align that south pole which is there in the armature with the north pole of the field, and the north pole which is there in the armature to align with the south pole, this armature will try to rotate. The armature will try to twist. The armature will try to move. So the armature will try to move like this. It will try to twist like this. Is it clear? Is it clear? So can I say as of now? Can I say as of now? In case of a DC motor, what is the reason that the armature will turn? The armature will twist, means I'll give the statement. So whenever you start giving the excitation to the armature winding, that armature windings and armature winding currents are forming poles in the armature core. And these poles, they seize an opposite poles in the field, and to align these poles with the field poles, the armature will try to rotate. The armature will try to rotate. So the intention of this armature is to align the south pole of the armature with the north pole and the north pole of the armature with the south pole. For that, the armature will try to rotate. Is it clear? Is it clear? Yes. Done. Now here I'll try to draw. So this is a north pole. This is a south pole. So this is a south pole, this is a north pole, right? So here this is an armature. So this armature is trying to rotate to align this south pole with this north pole and this north pole with this south pole. It looks like this armature starts moving. But once the armature starts moving, the conductor which is here will try to move here and it will try to come here. So when that armature conductor is moving from one position to another position, it looks like the south pole is moving. The south pole is moving to align with this north pole, and this north pole is moving to align with the south pole. But indirectly, when the south pole is moving, it will disappear. It will disappear. It will disappear. So when it disappears, assume that it disappears. So when this conductor is coming from this position to this position, again the direction of current will be changed. Again the same south pole will be formed there. Why? Because the direction of current in that conductor is again becoming cross. Again the polarities are remaining same. Again in the same place. Again in the same place. What is the pole that is formed here? South. Again in the same place. What is the pole that is formed there? North. So like that, it looks like the same south pole is reappeared there. Then this armature will further continues to rotate, hoping that it can align that new south with north and new north with south. Like that, you will try to further rotate. Once it further rotates, the other conductor will again change the position, again in the same place, again the same pole is formed. At every instant of time, there is a south pole formed. Then at every instant of time, this armature will try to rotate, hoping that this can that can align this south pole with this north pole and this north pole with the south pole. But that hope will remain hope only. Why? Because here the commutator is cheating. So it is something like this. I am calling myself as a field north pole, and I'm eagerly waiting that south pole will come and align with me. For this armature is rotating. But there the commutator is cheating. Why the commutator is cheating? Once this armature starts rotating, the positions of the conductors are changing. When the positions of the conductors are changing, then obviously the direction of currents in those conductors are changing. So because of the changes of current from dot to cross, so the same pole is reappearing in the same place. So it looks like the same south is standing there, the same south pole is appearing there. So this north pole is eagerly waiting. Or when you will come and align, so armature is doing hard work to align, but the commutator is cheating, so that remains hope only. So there is no chance that the south pole will get aligned with the north pole and this north pole will get aligned with the south pole, and hence that armature will continuously rotating, 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 rotating. Is this point clear? Right? So let me tell. Initially, why the armature will rotate? Simple answer. The armature rotates because of continuous attraction and repulsion. So between which two magnetic fields, there is a continuous attraction and repulsion. Between the field poles and between the armature poles, there exists a continuous attraction. There exists a attraction and repulsion. So because of that, this armature will try to rotate. But once it starts rotating, then the positions of the conductors are changing, and they are undergoing short circuit with the brushes. When they are undergoing short circuit with the brushes, the directions of current in those conductors are again changing. So they are making that pole to reappear in the same place, right? As the pole is reappearing in the same place, again, the same south pole is trying to attract with this north pole. Again, this north pole with this south pole, like that, with a hope this armature can align this south pole with the north pole, this north pole with the south pole. This armature will continue to rotate, 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 rotate. So this armature is a innocent fellow. That armature doesn't know that there is a commutator who is cheating by changing the direction of current in those conductors and making that south pole to reappear in the same place at every instant of time, and hence there is a continuous rotation of this armature. Is this point clear? Is this point clear? So if anyone questions you, as of now, or what is the role of a commutator as of now, I'm talking about at this instant, what is the role of a commutator? I can blindly say that the role of a commutator is to change the direction of current in a particular conductor which is undergoing short circuit with the brushes. For say a conductor is under south pole carrying a current outwards, when it is touching the brushes, the direction of the current will be into. It is changing into into. Similarly, if a conductor is carrying the current into, if it is short circuit the brushes, it is changed into dot. Right? Is it clear? Right. Now the question is, I need a continuous rotation. If I need a continuous rotation, then this attractive and repulsive forces should be continuous. If I need a continuous rotation, these attractive forces and repulsive forces should be continuous. So if I want to have a continuous attractive and repulsive forces, so this north pole has to see always which pole there? South pole. And this north pole has to see on the bottom a north pole, and this north pole has to see a south pole, and that south pole has to see a south pole. It is something like if you want to continuously talk to your friend, then your friend has to be next to you, right? So that you are stationary with respect to each other. When you are stationary with respect to each other, you can exchange the words and you can talk to your friend continuously. Here also, if I want to have a continuous rotation, then those attractive and repulsive forces should be continuous between the field poles and armature poles. Those attractive and repulsive forces should be continuous. If those attractive and repulsive forces has to be continuous, this north pole should always see a south pole, north south pole there, and this north pole has to see a south pole. So it has to see every time a north and south continuously. So if it has to see those poles continuously, means the relative speed between the two poles should be zero. Then only it can see. When the relative speed is zero, the poles are stationary with respect to each other. So tomorrow, if anyone questions you, are for the production of torque, the turning effect, why the relative speed between the two fields should be zero, then you can answer. If the relative speed between the two fields is zero, then those respective poles are stationary with respect to each other. When they are stationary with respect to each other, there exists a continuous attraction and repulsion. Because of that, there is a continuous rotation. Then there is a continuous rotation. Is this point clear? Is this point clear? Confirm me. Right. So as of now, I'm trying to answer to these two questions. What are those two questions? Why we need two magnetic fields? The answer for those two magnetic field means there should be attractive and repulsive forces. If I take a magnet, single magnet, so there is no concept of attraction and repulsion. If I'm having another magnet, if I try to bring two similar poles, there is a repulsion. If I bring two opposite poles, there will be attraction. So we talk about attraction and repulsion when we are having two magnets. So here also, as this armature rotates because of a continuous attraction and repulsion, so how many magnetic fields are required? Two magnetic fields are required. The next question is why the relative speed between the two magnetic fields should be zero. If I want to have a continuous torque, the relative speed should be, I need a continuous attraction and repulsion. Further, the relative speed should be zero, and hence the pole should remain stationary with respect to each other. Is this point clear? Confirm me. Is this point clear? Confirm me. Now I'm trying to update my statement. I'm trying to update my statement. Just I'll give break 2 minutes. I'll try to update my statement with respect to a commutator. So what is the role of a commutator? Means I'll try to give the statement like this. The role of a commutator is to maintain the relative speed between the two fields zero. Or how means, so it will try to change the currents in the particular conductors which are undergoing short circuit with the brushes. If the direction of currents are being changed, then the position of those poles are fixed. When the positions of those poles are fixed, then the relative speed between the two fields is maintained zero. So when there is no commutator, there is no attractive and repulsive forces continuous, there is no torque production. So what is the role of a commutator means? So I think in your BTech level you might have come across the role of a commutator is to change the direction of current, or in somewhere it is acting as a rectifier, AC to DC or DC to AC. But to be more precise, to be more clear, you can give these statements. What is that? The role of a commutator is to change the direction of current in a conductor which is undergoing short circuit with the brushes. If it is doing that, then it is making the relative speed between the two fields zero by making the poles stationary with respect to each other. When the poles are stationary with respect to each other, there exists a continuous attraction and repulsion. Because of that, there is a continuous rotation. I hope this point is clear. All of you confirm me. Right. So as of now, before we leave for a break, I'm just keeping 2 points to be noted. One is how many magnetic fields are required? Two. Why? There should be attraction and repulsion. Second point is the relative speed between the two fields should be zero. Why? If the relative speed between the two fields is zero, the poles are stationary with respect to each other. Right? When poles are stationary, then there exists a continuous attraction and repulsion. Because of that, there is a continuous rotation. So we'll take some break. After that, I'll come back, please. Thank you.
I'm back now. So, so please confirm with my audio, video, and other things if they are clear. Right. So, can I say for the production of the turning effect, how many magnetic fields are required? Two magnetic fields are required, and the relative speed between the two magnetic fields has to be 0. So, in case of a DC motor, who is trying to maintain the relative speed between the two magnetic fields 0 means a commutator. How? By changing the direction of currents in a particular conductor. If the relative speed is 0, then the poles are stationary. If the poles are stationary, then there exists a continuous attraction and repulsion. Because of that, there is a continuous rotation. So, can I give a statement like this? If the relative speed between the two fields is 0, then the poles of the respective fields are stationary with respect to each other. Hence, there exists a continuous attraction and repulsion, due to which there is a continuous rotation. Continuous rotation. I hope this is clear. Confirm me, all of you. Confirm me, all of you. It is clear. Right. So, two questions we had answer for those two questions. One is how many magnetic fields are required? 2. Why the relative speed between the two fields should be 0? We have seen. Now, the next question is the poles on the stationary part, the poles on the rotating part should be same. In this case, if you observe, how many poles we have designed on the field? 2 poles. And how many poles we have designed on the armature? 2 poles. We can see poles are same. Now, for example, if I'm designing more than 2 poles, what happens? See, let us see. I'll be considering an armature like this, which is designed for 2 poles. What are those? Let it be south, let it be north. Then I'm having a field pole north and I'm having a field pole south. Then you can see there is a attraction, there is a repulsion, there is a attraction, there is a repulsion, and hence there is a continuous rotation. So can I say if the poles are same, then those attractive and repulsive forces. So this is attractive force, repulsive force, attractive force, repulsive force. Those attractive and repulsive forces are acting in the same direction, and hence those forces are additive, and hence the rotor will, or the armature or the rotating part will continues to rotate. Right? Is it clear? Confirm me. Confirm me. Right. But fortunately or unfortunately, here what I'm trying to do means I'm designing a armature with 4 poles. What are those? N1, let it be S1, N2, S2. Let me consider. So here I'm having some 2 poles. 2 poles. Let me consider 2 poles. Now you can see, so something like these are aligned. So I'll draw a little bit like this. So it is S1, N1, S2, N2, something like this, right? Then you can see what exists between these two: attraction. So if it has to move like this, then what exists between these two? Let me draw clearly. So these are something like unequal. Just give me time. Right. See. So in which direction it will rotate? Please see, observe here. Here also I need to apply the law of magnetism. So this is one field axis. This is one field axis, right? So what is existing between these two? Attraction. Very good. If there is this exists an attraction, this has to move like this. But at the same time, what is existing between these two? Attraction. So these two forces are acting in opposite direction. At the same time, what is existing between these two? Repulsion. But what is existing between these two? Repulsion. Then you can see these forces and these forces are acting in opposite direction, and hence the resultant force acting on the rotating part will be 0. So that is the reason, very compulsorily, when you are designing these DC machines or induction machines, you have to see that the stator poles and the rotor pole should be same. If the stator and the rotor poles are same, though the attractive and repulsive forces are additive, and because of the additive forces, the rotating part will rotate. But whereas in case of, if the poles are unequal, though the attractive and repulsive forces are cancelling out, and hence the torque acting on the rotating part will be 0. Is this point clear? Confirm, all of you. So can I give a statement like this, please? 1 second. Right. So can I give a statement here? If the stator and the rotor poles are same, if the stator poles and the rotor poles are same, attractive and repulsive forces are in same direction and are additive. Therefore, the rotating part continues to rotate in that particular direction. So if the stator and the rotor poles are unequal, then attractive and repulsive force are acting in opposite direction, and hence the resultant force is 0. The rotor cannot, or the rotating part cannot rotate. So if the stator and the rotor poles are unequal, attractive and repulsive forces are in opposite direction, hence the net force or torque acting on the rotating part is 0. zero. So that is the reason when you are designing these DC motors, induction motors and synchronous motors, you have to see that the stator and the rotor pole should be same. Otherwise, there is no concept of motor. Then you may have a doubt. Sir, during our graduation, BTech, we came across reluctance motor or stepper motor. There, we have seen that the stator poles and the rotor poles are unequal, something like this. If you just take an example of a stepper motor, it is 8 by 6. Just an example. What is the meaning of 8 by 6? There are 8 poles on the stator and there are 6 poles on the rotor. So there, for motoring, for twisting, the pole should be unequal, wiser. The reason is, so whatever the motor I'm talking about, the DC motors, induction motors and synchronous motor, they works on electromagnetic torque. What is that electromagnetic torque means? The current carrying conductor placed under magnetic field will experience as a force. That also I'll show, don't worry. Experiences a force. Because of that, the so-called as the rotating part will rotate, right? But whereas in case of the so-called as reluctance motors or stepper motor, we don't have any current carrying conductor. So there the torque principle is a reluctance torque. So there in case of stepper motor, as the working torque is a reluctance torque, the poles has to be unequal. But here in case of induction motor, the working torque is a electromagnetic torque. What is that electromagnetic torque? The current carrying conductor placed under magnetic field will experience as a force, right? So I hope this point is clear. So can I write the above two conditions are applicable for the motors which works on electromagnetic torque. Electromagnetic torque. Nothing but your Lorentz law. So this is something about the concept of pole formation in which motors? DC motors. Is this point clear? Confirm me all of you. Right. Now I'll be explaining somewhat in detail. So why this armature will rotate? So if you just look into this example, so from this you can see this armature is trying to rotate in which direction? Counterclockwise direction. It is clear. The same logic and the same concept can be explained with the help of your Lorentz law and with the help of your Fleming's left hand rule. Just give me 2 minutes time, I'll tell. So according to your so-called as Lorentz law or motor law, what is that principle? F is equal to BIL. So if you want to have motoring, then what are the conditions we need to satisfy? B, L, and through that L, there has to be some current I. So if these three conditions are being satisfied, then there will be a force acting, and because of that force, the rotor will or the armature will rotate. So in case of DC motor, how these conditions are being fulfilled means the first condition is magnetic field. So we have produced with the help of a field windings and field current. Done. The first condition is over. I'm talking with respect to Lorentz law. First condition is over. What is the second condition? I need a conductor of finite length. So what I'm trying to do means I'm trying to take a armature, and in the armature I'm placing the conductors. Just I'm taking only a pair, and those ends are being brought out. And with the help of some external source, I'm trying to supply current. So these are the conductors of finite length carrying a current. Then you can see these are the conductors which are carrying current and they are under magnetic field. So these conductors will experience as a force. If I'm calling conductor A, conductor P, both will experience a force. Why? Because through that conductors we are passing a current, and those current carrying conductors are under magnetic field. So those conductors will experience a force. Is this point clear? Confirm me. Is this point clear? Confirm me. Yes. Right? Done. Now the question is in which direction that rotates. So for that, which rule I need to apply? Fleming's left hand rule. This is my left hand. If I place my forefinger in the direction of field, middle finger in the direction of current, then the thumbs gives the direction of force. With respect to this, field is like this. The direction of current is into the force, the torque will be like this. So there will be a twisting force on the conductor. Move, move, move. Like this, the conductors will try to move. So whenever the current carrying conductors are under the magnetic field, so this armature will try to move like this. Is this point clear? Confirm, confirm me. So I can explain in other way also. In other way also. What is that other way? See, many ways you can explain motoring. What is that? The magnetic field lines always try to take a low reluctance path, always. Low reluctance path, always. Now see, when I'm not having any armature, so these magnetic fields will try to take the shortest path. What is the shortest path? The straight path like this. Straight path like this. Like this. But whenever I'm having a conductors here, so these conductors I'm showing here. Conductors here. And if these conductors are carrying a current like this, so because of those current carrying conductor, we are having one more field. So which rule I need to apply? Right hand thumb rule. So if I apply that like this, so if I apply this like this, then the magnetic flux lines which are supposed to take the shortest path, they will come like this. They'll come like this. So because of those current carrying conductor, there is a diversion in the path. Then this field will say, "Arey, you stupid fellow, you are occupying our place. Please move from this position, move this position." So this armature will try to rotate like this. It will rotate like this. It will rotate like this. Is this point clear? Confirm. Right. Done. So this is something about the so-called as the concept of magnetic field, right? With respect to which motor? DC motor. As I told you that after this concept, you are supposed to answer to these three questions. What are those three questions? One is why we need two magnetic fields, why the relative speed between the two magnetic fields should be zero. Third one is why the poles should be same. So if all these questions, if you are able to answer, then I can go for the next topic. Please raise the hands if you have followed this. Please, all of you raise the hands. Right, done. Now I'll be talking about next AC motors. AC motors. AC motors. AC motors. So if I'm correct, most of you might have completed this BTech course, right? And you are taking this GATE coaching. And in your BTech, somewhere in your second year or somewhere in your third year, you might have come across this induction motor or induction machine subject. So in that induction motor, say there is one question, numerical. So let me see how many of you will answer to this question. Then after that, we can go for this AC motors, right? I'll ask one question. The question is a three-phase 400 volts, 50 hertz, 6-pole induction motor, dash, 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 dash. So I'm considering about the poles here, poles. How many poles are given here? 6 poles. So what do you mean by that 6 poles? Please try to answer. So I'll give options, sir. Actually, there are 2 poles per phase. I'm talking about the data given. 2 poles per phase. As it is a three-phase induction motor, 2 into 3, 6 poles per phase, right? That is one option. Option B, no sir, whatever the poles information that is given, all the poles are per phase. Option C, sir, don't know. Don't know. So now please get ready with your question and answers box and you try to tell which one is the correct answer, A or B. A or B. So let me see. Right from here I'll see. Yeah. See how four poles are formed. I have taken an example, Baba. It is not four poles are formed. So most of you A, B, B, C. Okay, C also there. Okay, don't know. B, A, C. Don't know. Okay. B, A. So most of the answers are A. Most of the answers are A. Okay, please stop. Don't post again. Most of the answers are A. So let me just go with your answer A. You can just clarify whether it is correct or wrong. If I'm going with A, let us see. See, in one more exam, in one more numerical, the data is a three-phase, 400 volts, 50 hertz, four-pole induction motor. Then if those who are given option A, then according to you, it is 4 by 3. 1.33333 into 3, it is something like 4 poles. So please remember option A cannot be correct. So the which option is correct means option B. So whatever the information that is given will be always the poles per phase, right? Please remember it is poles per phase. So if I'm trying to explore the data given here, so here it is given as a three-phase supply. So what is the meaning of three-phase or three-phase means? So whatever the supply I'm trying to give to that motor is a three-phase supply. So it is IA, IB, ICB, whatever it means, three-phase supply I'm giving. And what is that line to line voltage I'm applying? 400 volts. Then what is that 50 hertz means? Whatever the currents that flows in each winding, IA, IB, IC, the frequency of each current is 50 hertz. He will not mention. So the frequency of phase A current IA is 50 hertz. The frequency of current IB is 50 hertz. The frequency of current IC is 50 hertz. He will not mention. So it is understood that 50 hertz means the frequencies of all those three currents is 50 hertz. Is this point clear? Similarly, what is that 4 poles or 6 poles means? So if you are having three phases, each phase is designed for 6 poles. He will not say phase A is designed for 6 poles, phase B is designed for 6 poles, phase C is designed for 6 poles. So he'll give it is 6 poles per phase. So indirectly it says that 6 pole induction motor means each phase is designed for 6 poles. So please try to rule out that whatever the information that is given 6 poles is not the total poles. It is the poles per phase. Poles per phase. We are not supposed to talk the total poles. Total poles will not exist. Only poles per phase we need to talk. So in this case, how many poles are there per phase? It is something like 6 poles, right? Is this point clear? Confirm me, all of you. Right. Now, as we define poles per phase, poles, which option is correct in this? This is correct. As we define poles per phase, one should have clarity what is called as a phase. So many times you are coming across all this terminology, phase, winding, like that. What do you mean by phase, right? Let me explain what is called as a phase. Please try to understand. So for that, I'll be taking a generator. So on what principle this generator works? On Faraday's law. What is that? Faraday's law says that if I'm having a conductor of finite length L, if it is moved with a velocity v under a magnetic field D, so that conductor will have a EMF. Or if a coil is moved under a magnetic field, if the flux linkages with that coil changes, an EMF is induced. So in cut short, I'm trying to tell like this. So I need a magnetic field first. So where is that magnetic field? So I'm talking about a DC generator 1C. I'm having a magnetic field, north pole and south pole. First condition is over. What is the second condition? I need a conductors of finite length. So I'll be taking a rotating part called as a armature, and on the armature I place two conductors AB and two conductors CD. Just I'm considering, and those ends are being taken out with the help of a commutator and pressure end. Second condition is also over. What are the last conditions? Those conductors has to be moved with some velocity. So here I mechanically couple this to some external prime mover, and with the help of this external prime mover I rotate the armature. So whenever I rotate the armature, so these armature conductors will rotate. When they are rotating, they are cutting the magnetic flux lines, and hence our EMF is induced. So this is what we are doing in any generator. So the magnetic field lines are forced to cut the conductors, then an EMF will be induced in that conductors. Is this point clear? Confirm me. Now I want to know the direction of induced EMF. For that, which rule I need to call upon? Right hand thumb rule. So all I pre-assume that you know right hand thumb rule. If I apply right hand thumb rule, so in this it will be cross, and in this it will be dot. If you apply the right hand thumb rule, you can just apply that. It is not a big deal. So this is the concept of a generator. I'll draw this in a more exploring way. What is that? See here. Please understand this. I'll be taking this north pole here, this north pole. See, all this is to explain phase. If you don't know phase, then you cannot understand any concept of pole formation in AC machine. Please remember. So this is a north pole and this is a south pole. South pole. So how many conductors are lying under this north pole? Two conductors. Let me show it like two conductors. This is one conductor A. This is one more conductor B. Similarly, I have one conductor C under south pole and one more conductor D. D like this. A, B, C, D. So I'm drawing just for convenience purpose. So how many conductors are there? See, if I'm calling this one as a field, this one as a conductor, you can see only circuit. So whenever I move this conductor, so these conductors are cutting the magnetic flux lines and hence an EMF is induced. So I'm drawing those conductors, right? Is this clear? This figure is clear. Second figure is clear. Confirm me. Right. Only few, what happened to other? All of you raise the hands. It is a simple thing. Right, done. Now, whenever I move the conductor, basing on the length of the conductor, basing on the velocity with which we move, basing on the field intensity, the voltage per conductor will be 2 to 5 volts. Voltage per conductor will be 2 to 5 volts. So let us say in our case, the voltage per conductor is 5 volts. Let us consider 5 volts. I'm talking about small rated machine, 5 volts. Let us consider 5 volts. Then, if you observe here, the conductors which are under north pole are having polarities plus minus. Let us consider. And here minus plus, minus plus, like this. This is done. But if you take any generator, so the generator will be having a voltage of 230 volts. So no generator will have directly 230 volts in a single conductor. So small voltages will be generated, and those voltages are being added up to form a voltage of 230 volts. So if I want to have a voltage of 230 volts, what I need to do means I need to add up all these individual conductor voltages, right? So for that, what I'm trying to do means I'm trying to add or join these two conductors, say A and B I'm trying to join. When I'm trying to join those two conductors A and B, so what is the voltage I'll get here? You can see this is minus low potential to high potential. When I'm talking about minus to plus, so we take it as a rise, low potential to high potential rise. So rise of 5 volts. Again from here, so we are having 5 volts, but again from 5 volts, we are coming from plus 5 to minus 5. It is again drop. So what is the voltage we are having here? 0. So what is observation you can see here? So if you want to add up the voltages, you are not supposed to connect the conductors which are lying under the same poles. So you need to change this. What is that? I'll just break this. And what I'll try to do means I'll try to connect like this. I'll try to connect like this. I'll try to connect like this. Then you can see low potential to high potential is rise. Again, low potential to high potential is rise. Again, it is minus 2 plus rise. So what is the voltage I'll get here? The voltage what I'll get here is 10 volts. This we call it as one turn or one turn. So after one turn, what is the voltage we are having here? 10 volts. Is this point clear? Confirm me. Is this point clear? Confirm me. So a single turn will consist of how many conductors? Two conductors. And please remember that these two conductors are under opposite poles. That is the reason if you consider any two conductors of a particular turn, particular coil, for full pitch, what is the angle between those two will be 180 degrees. The reason is, so in a turn, we are adding the voltages. If I want to add the voltages, so these two conductor sides should be in opposite poles. So if they are supposed to be in opposite poles, then electrically what has to be the angle between them? 180 degrees electrical for full pitch. Is it clear? Confirm me. Is it clear? Right. Now what I will do means I'll continue this. I'll continue this and I'll go for the second turn like this. Then what is the voltage I'll get here? 20 volts. 20 volts like this. 20 volts like this. So this I call it as a coil. I call it as a coil. So in this coil, how many turns we are having? 2 turns. Then what is the voltage I will get across this coil? It is 20 volts. So can I give a generalized statement like this? If you want to decide the voltage across a coil, first I need to decide what is the voltage across a single conductor in this case. So in this case, the voltage across a single conductor is 5 volts. Then the voltage across a turn is a 10 volts. Then in this particular coil, how many turns are there? 2 turns. That is the reason the voltage across that coil will be 20 volts. So can I say if I want to decide the voltage across a coil, I should know the voltage across each turn. If I want to know the voltage across each turn, I should know the voltage across each conductor. So in this case, the voltage across each conductor is a 10. Then the voltage across a turn is 10 volts. Then voltage across a coil is 20 volts. Is this point clear? Confirm me. Confirm me. Right. Like this, if I'm going for 23 turns, 23 turns, then what is the voltage I'll get here? 230 volts. What is the voltage I'll get? 230 volts. Is this point clear? Is it point clear? Right. Now see on what basis the output is this point clear? If I'm having 23 turns, the voltage across each turn is 10 volts. The total voltage will be 230 volts. Is it clear? Confirm me. Right. See, now here I'm just designing the output here of this generator. So in this generator, I'm having 23 turns. Then voltage what it can give is 230 volts. Then whatever the coil I have designed, so those windings have the capacity to withstand the safest current of 1 ampere. So up to what ampere it can withstand means say 1 ampere. The winding size and other things we have designed like this. Then I can say, so this generator can give a output power of 230 volts. when the voltage is 230 volts, when you are loading the generator with a current of 1 ampere, then we call it this one as the output rating. So how much power this generator can give? 230 watts. Why? Because the generated voltage is 230 volts when the windings are loaded to carry a current of 1 ampere. For example, if you are connecting very light load, say the current is zero point 0.1 amps, then what is the power it is feeding to that load? It is only 23 watts. If you are increasing the load, current will increase. When current is increased, so the power supplied to that load will also increase. Like that, we design the ratings of a generator. Is this point clear? Right. Now, but I want more voltage. So if I want to have more voltage, what I'll do means I'll connect two coils in series. Then in this case, what is the voltage I'll get? 460 volts. If the two coils are connected in series. Then instead of series, I need to have more current. Then I'll connect the coils in parallel for high current. And I can go for series parallel connection for more current and for more voltage. So this entire configuration, we call it as a winding. So if you look into any windings of a generator or any winding of a machine, you can see the series and parallel connection of coils. And in the coils, you can see there are turns. And in the turns, you can see there are conductors. And you can see these conductors are 180 degrees apart for full pitch, right? So if anyone questions you, what is a winding? Winding is nothing but series and parallel connection of coils. And coil is nothing but series of turns. Turn is nothing but two conductors which are placed 180 degrees apart. Is this point clear? Confirm me, all of you. Is this point clear? Confirm me. Right. Now I hope you understood what is called as a winding. Then what is called as a phase? Phase. So a phase is nothing but a winding. So we can exchangeably use the term phase or winding. Right? Sorry. We can use phase or winding exchangeably, right? So finally, can I give a statement? Two conductors joined with some end connection will form a turn. Such a turns connected in series will form a coil. Such coils connected in series and parallel will form a winding, and a winding is nothing but a phase. When I'm talking about a three-phase, means there are three windings placed on the stator, and those windings will be having series and parallel connection of coils, and those coils will be having turns, and those turns will be having two conductors which are under 180-degree shift. Is it clear? Confirm me, all of you. Confirm me, all of you. Yes. So can I say two conductors? I'll write a note here. Two conductors. See, I'm trying to take you from scratch. Understand that two conductors forms a turn. So whenever I'm talking about turn for a full pitch, the angle between the two conductor side should be 180. Why? We are adding the voltages. When we are adding the voltages, the angle has to be 180. Why? Because they should be under opposite poles. Two conductor forms a turn, and such a turns connected in series forms a coil. Such coils connected in series and parallel forms a winding, and a winding refers to a phase. Is this clear? Confirm me, all of you. Confirm me, all of you. Right. Now I'll be defining some terminology. Active length. and inactive length. So this length we call it as active length. Why that is called as active length means only that section of the conductor cuts the magnetic flux lines. Only in that section an EMF will be induced. And this section we call it as inactive length. Why? Because that section is will be on the back side of the armature. So that will not cut any flux lines and there is no EMF induced in that. But still we need to add up the voltages. So that we call it as inactive length, or we can call it as end connection, or also we can call it as overhang. 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 Please try to remember all these terminologies. So active length means it is a section of the coil which cuts the magnetic flux lines and hence an EMF is induced. What is that inactive length? It is a section of the coil which is used to add up the voltages, right, to form a coil and to form a turn. Is this point clear? Confirm me all of you. Confirm me all of you. Right. Now, what I'll try to do means I'll consider now AC motor. As I told you that in AC motors, always we design poles per phase. Poles per phase. So first what I'll try to do means I'll consider a single phase and I'll try to explain the formation of poles in that single phase. After that, I'll explain the remaining things. So almost it is 8:30. So I'll stop for today. So I'll follow the time. Why? Because we need to discuss the doubts also. So if I stop, I can spend some maximum time with you. Yesterday it was like 9:30, around 9:20 like that I left. So if I stop at 9, it will be 10. That is not good. Anyhow, I'll stop. So I hope you understood today's class. All of you raise the hands. Raise the hands. Right. So we'll have doubt discussion. Let me bring that earphones. Give me some time, 1 minute. Yes. So first let me see the questions from this box. Right. Full pitch means if the angle between the two conductor sides is 180 degrees, that is full pitch. I'll explain more tomorrow. Don't worry. Sir, for a machine, which is the best as leakage flux should be more or mutual flux? Mutual flux should be more. If the leakages are more, the performance will come down. Yes. So in case of other machines also the air gap has to, what is the question means, sir, only in induction motor it is the least air gap. Compared to other machine, the air gap should be less here. So that I'll explain that poles per phase tomorrow when I'm trying to explain the concept of pole formation tomorrow, right? So what is the poles per phase means? See, so whatever the data that is given on the nameplate details represent the poles per phase only. Now we are going to see how to design poles per phase. So if I want to explain the poles per phase, first of all, you should know what is called as a phase. Then this is what we have seen, what is called as a phase. After that, we'll see how to design poles per phase. Then after that, the three-phase poles we are going to discuss, right? Done. 1 second. Right. So adding of conductors under adjacent poles should be opposite poles. Then only we can add. Otherwise, we cannot add the similar poles. Please remember. If there is no commutator in induction motor, how the rotor rotates, I'll explain that. So whatever the discussion we had as of now, it is only the DC motor. We have not discussed about induction. I'll explain then without a commutator how the rotor will rotate in induction, you can see. Why leakage flux are different in open slots. Already you can refer the notes. In open slots, you can see the air gap length is less compared to the slots width. That's the reason the leakages are less. You can refer that. Why the currents in armature conductor changes, it's from dot to cross. So all these are your DC motors. The role of a commutator is to change the direction of current. So you can ask all these in, details in your so-called as DC motor, right? Let us go for now. Sir, while explaining the doubts, please refer English only. Okay, right, other people's, done. Fine. Now I'll give the scope for those who want to have doubts. Right. Sirisha. Hello? Sirisha, you are there? No. Next, Imtiaz Pasha. You are there? Haan, Baba.
Good evening, sir.
Good evening, Baba. Please.
Sir, hello, sir.
Yeah, Imtiaz Pasha. I can hear you.
Sir, I have general doubt in DC generators.
See, Imtiaz Pasha, if it is a general doubt, you can talk on my mobile. If it is related to today's topic, you can ask now. Is
Yes,
it
sir.
okay?
Today's topic, sir.
Yeah, please ask.
Sir, rotor is rotated with the prime mover, no, sir.
Here, not rotor. In case of a generator, we call it as armature, right? So you mean to say this one?
Yes,
Yeah.
sir. Armature,
Yeah, please.
armature is rotated with the help of the prime mover.
Absolutely correct.
Due to that,
The armature
cutting,
conduct flux cutting
flux.
will take.
Sir, the north and south poles are there, no, sir.
These are the field windings poles.
Sir, how they form, sir? North
See,
and south pole.
already I told you, na? So you can see here how they are formed.
Sir, but generators means we have taken input, output as a current, no, sir.
No. See, even in case of a generator, we need field current to produce the magnetic poles. So this is required even in case of a generator also. I think in my last class I told you that there is no separate construction for motor and generator, right? So
Yes, sir.
if you want to use this machine as a motor now, this machine, so instead of driving the armature with a prime mover, if you pass currents into the conductors, then the current carrying conductors will experience a force and it rotates. But we need EMF. So for that we have to move the conductors. The field is required there. So
Okay.
how this field is produced? So here we are placing a coil,
Yes, sir. Yes, sir.
and through that coil we are giving a DC. like this. Then magnetic field is produced. First condition is over. The second condition is I need a conductors of finite length. Third condition is I need to move. Is it clear, Imtiaz Pasha?
Yes, sir.
Right, Baba. Right?
Okay.
Right. Thank you. Right. Soundarya Vishal. Yes. Yes. Hello. Can you hear me?
Hello, sir.
Ama. Yeah, please ask.
Mm. Sir, I want contact number, sir.
Yesterday I have given Nama.
I am not written, sir.
So I'm writing on the board, you can take. Can you see on the board?
Okay, sir.
Taken ma?
Yes, sir. Okay, sir. Thank
Right
you,
ma.
sir.
Right ma, right. Pranay.
Sir.
Pranay.
Hello, sir. Hello, sir.
Hello Pranay.
Hello, sir. Is it audible to you, sir?
Hama, you are audible to me, please.
Yes, sir. Sir, in the case of stator and rotor poles are unequal, so can you please explain once that concept, sir?
See. So this is your case, right?
No, no, sir. This before this, when two pole stator and rotor pairs, sir.
The,
Yes, sir. This one, sir.
yeah. Now you can just, law of magnetism, right?
Yes, sir.
Yeah, please. So like poles,
Like poles repel each other,
very good. Unlike poles,
attract each other, sir.
excellent, excellent. Now you please tell me. So what is existing
Yes,
between
sir.
this? What is existing between this S1 and N? Attraction.
Yes, we will here. Attraction, yes, sir.
Excellent. And what is existing between this N and N2?
N and N2,
Repulsion.
repulsion, sir.
Excellent.
Yes, sir.
So this side of the armature wants to rotate in which direction? Counterclockwise direction, correct?
Yes, sir. Yes, sir.
But at the same time, what is existing between this N1 and S?
Attractions,
At the same time, what is existing between this S and S2?
repulsion. Yes,
So
sir.
this side of this armature wants to move in which direction? Clockwise.
Yes, sir. Clockwise direction. Yes, sir. I got it, sir.
Is it clear, Baba?
Yes, sir. Sir, but two forces are equal, so it
But-
will be in constant position.
But they are
Torque
acting.
is zero.
They are acting in opposite. Yes, the torque is zero. Is it clear?
Yes, sir. But unequal forces means it will rotate now, sir. If
So the forces cannot be unequal. Why? Because the currents are same, the number of turns are same. The forces cannot be unequal. Why? Because when we are passing the currents, armature current is same. The turns the part of the turns will be same. So forces cannot be different. If according to your will, if the forces are different, there is a possibility that it can rotate. But the forces cannot be different here.
yes, sir. Yes, sir. One thing, sir. Sir, if the poles of stator and rotor are unequal, so that some force will be there now, sir.
But I mean to say those forces are acting in opposite direction. When they are acting in opposite direction, see, I myself call as it as a rotor or armature. So
Yes, sir.
on one side, one person want to move me in this direction. On other side, another person wants me to move in this direction. Both the forces are acting, magnitudes are same, but they are in opposite direction. Then where I stay,
Constant.
the
Zero
same,
position, sir. Yes, sir.
the same thing is happening here also.
Yes, sir. Sir, but I am telling that if the poles are unequal, so some force is there now, sir.
But there is no concept of forces are unequal. The forces magnitudes are same now here. The
Yes,
forces,
sir. Yes, sir. Poles are unequal. I am asking like that, sir. If the poles, stator poles are 6 and rotor poles are 4, so how there will be some force exist?
no, see, if you can apply the same logic. You take 6 poles and you apply 4 poles. There is no concept of motoring. So here how many poles have taken?
4.
And how many stator poles I have taken?
Stator 2, sir.
And you apply for any number, like you take 6, 4, like that you take. So there is no motoring. So opposite forces will cancel out. Understood?
Yeah, okay, sir.
But if
Sir,
you look,
and one small thing, sir.
huh,
Yes.
yeah, please.
Sir,
Pranay.
sir, you said that air gap is smaller for the induction motors. Is
Huh.
the same applicable for all motion motors like DC motors and like synchronous also? Like same thing, sir?
See, generally we are supposed to maintain smaller air gap. But whereas in case of a synchronous motor, so we try to maintain little bit larger air gap. The reason why we are maintaining little bit larger air gap means it may be a synchronous generator or synchronous motor. They are over excited all times. Over excited. When they are over excited, the amount of flux in the air gap will be more. Why? Because it is a separately excited motor. Flux will be more. If the air gap is less, if more flux is accumulating, if more flux is present, then cores will get saturated. So for that, so the comparatively in synchronous machine, the air gap length will be more. Understood? So
Yeah.
basing
Yeah,
on
okay, sir.
basing on the type of the machine, we need to decide. It is not like in all cases it should be less. So comparative, anyone questions in which motor it will be less means induction motor you have to tell blindly. Understood?
Yes, sir. Yes,
Right.
sir. And
Right.
sir, one small doubt, sir.
Ah.
After this AC motor title is there, so 6 poles like that you said, sir. So after that, can you please once briefly explain once again, sir?
I didn't get you. See, Baba, Pranay, when I told you that you can go through, so it is not the question of explaining for each and everything. So you can do it now. What
Sir,
is
little bit. Yes, sir.
no, no.
These concepts, sir. Winding.
See, if you take how many poles you want there, you try. Why? Because it is something like you have to try, Baba. 6 poles you can draw. What is there? So N1,
Yes, sir.
S1,
Yes, sir.
then N2, then S2,
Yes, sir.
then N3, S3. Correct?
Yes, sir.
Then how many poles here on the rotor? How many poles on the
6.
rotor? This is 6, okay. On the rotor,
Yes.
on rotating part, how many poles? 4, right?
How, sir?
Yes, N1, S1,
Yes.
S2, N2. Let me take. Understood?
Okay, sir.
See,
Okay, sir.
what is existing between these two? Just I'm taking one. Repulsion.
Attractions.
Repulsion between S and
Yes.
S.
Okay.
At the same time, what is existing between these two? S2 and N2.
Yes, to attractions, sir.
Then in which direction both are acting?
Opposite directions.
Then what happened to the rotating part?
0. It does
Cancel.
not rotate.
Right? You can try for any number now. Is it okay?
Okay, okay, sir. Thank
Right.
you, sir.
Right, Baba. Good luck.
Thank you, sir.
Right, right. Right. Nilesh. Nilesh. Nilesh Ramesh.
Hello, sir. My doubt was clear, sir.
Clear.
Actually.
Okay, Baba.
Okay, sir.
Right. Right. Pratyush.
Sir, you have said the leakage flux is the either the flux that link with either the stator or rotor, no, sir.
Ha, Baba. Correct.
Sir, I have understood it, how it links with only stator, sir. But how it links with only rotor, sir?
See, when the rotor currents are induced, so there will be one more flux. Now see, whenever these poles are rotating, then definitely that will links with the rotor circuit, right? So that we'll see in the
Yes, sir.
working principle. When it links with the rotor circuit, what is induced?
EMF is induced, sir.
Then if the rotor circuit is closed, what circulate?
Current, sir.
Because of that current, one more flux is there. So that flux will be linking with the rotor and also linking with the stator and the rotor. So there we call it as leakage flux with respect to rotor circuit. Understood?
Okay, sir. Okay, sir.
Right, Baba.
Thank you, sir.
Right, Baba. Right. Right. Sai Charan Reddy.
Hello, sir.
Ha, Baba. Sai Charan Reddy, please.
Sir, in disadvantages, in disadvantage, you said about something like
In this,
corona. You compared with the corona discharge.
yeah, yeah. See, just I took one example. In case of your power system, you might have come across corona concept, right? In power system, you remembered?
Yes, sir. Yes, sir. But I did not understand in this case, sir. In our
See,
message,
Baba, what is corona? So in case of power system, the size of the
I,
conductor will increase, correct?
yes, sir.
But
Ionization.
yeah, that means you are increasing the true length or it is a virtual length, virtual area.
Virtual, yes, sir. Virtual area.
Correct. So here, what is the true length of the air gap? So this is the true length of the air gap, correct?
Sir,
This is the true length of the air gap, smaller length.
sir, between slots or between stator and rotor, sir?
See, actually, it is the radial length between the two cores. So this is the core actually. But because of this air, what happened to that amount of air in the air gap? So air is
Increase.
generally air has to be present here, correct? But
Yes, sir. Yes, sir.
this air is also adding. Then what happened to the total air?
Increase.
What about the average length if the air length is increased? What?
Average length means air gap average length, sir.
Yeah, air gap average length, correct.
Air gap average length increase.
Yeah, very good. That means the length which is supposed to be this much will try to looks like this much. So this much length it looks total. This much length it looks. That means it looks like the air gap length is increased or it is the same small
Air gap increases.
increase. See, I think in your circuits you might have calculated average values,
Yes, sir. Yes,
correct?
sir.
If
Yes,
it
sir.
is 2 volt, if it is 10 volts, what is the average value? It is more in between 2 and 10, correct?
Yes, sir. Yes, sir.
So it is minimum length, maximum length. So the average length will be in between somewhere. So it looks like the average length is increased, correct?
Yes, sir. I did not understand. You kept two arrows, now, sir, between these lines, sir. White color arrows.
So I mean to say that this is the original length, but because of this air, what happened to this average length? It is increased or it is same? So this is the minimum air gap. This is the
Yes,
maximum.
sir. Yes, sir. Yes, sir. That gap is between stator and rotor.
That looks like it is increased.
Yes, sir.
Sai Charan Reddy. Understood,
Yes,
ma?
sir. Yes, sir.
Right, Baba. Right.
Sir.
Yeah.
Sir, yesterday you told about in the induction machines there will be a current flow through yoke, no, sir.
In
In
induction
the
machine,
standardization of that frame, sir.
selection of frame.
Yes, sir.
Hmm.
Sir, in that you told something like that frame contain the frame due to current flow, the heat will be generated.
So not current flow in the core, not in the frame. Inside the core, there will be some EMF induced. Why? Because the flux linkages are changing, correct?
Yes, sir. Yes, sir.
So due to that EMF, what circulate?
Current.
Current. So if that current is flowing inside the
Okay.
core, that core will get heated up, right?
Heat. Yes, sir. Yes, sir.
That loss we call it as eddy current loss, correct?
Yes, sir. Sir, in leakage flux means phi L, na, sir. Leakage flux means.
Phi L, correct.
Means that phi L is represented at inductor, sir.
Equivalent to inductive drop.
Yes, sir. Yes, sir. Exactly. Yes, sir.
Understood?
Okay, sir.
Right, Baba. Right. Right. So no one is raising the hands. I'll stop for today.